Please subscribe to support the channel. Among the endless sea of stars that fill the universe, some capture our imagination more than others. Astronomers have catalogued countless suns, each with their own mysteries, but among them, one stands apart, not for being the closest, not for being the brightest in our night sky, but for being the most massive star ever discovered. That star is our 136A1. When scientists look out into the cosmos, they often ask questions about the extremes. What's the smallest? What's the hottest? What's the most powerful? Our 136A1 is the answer to one of those questions. It is the heavyweight champion of the stellar world, pushing the limits of what nature allows. To call it extraordinary would be an understatement. This single star embodies the very edge of possibility, holding secrets about the universe that continue to challenge and refine our understanding of how stars live and die. When we talk about a 136A1, we're talking about an object so massive and so luminous that, by all rights, it almost shouldn't exist. For decades, scientists believed there was a theoretical upper limit to how large a star could be before the very forces inside it would tear it apart. Yet, our 136A1 seems to have stretched those limits beyond what we thought possible. Its existence isn't just a fact of astronomy, it's a mystery, a puzzle that asks us to rethink the very physics of star formation and evolution. And for anyone curious about our place in the cosmos, learning about a 136A1 is like peering into the raw power of creation itself. This star is not a household name like Betelgeuse or Polaris, but among astronomers, it holds legendary status. It is the kind of discovery that reshapes textbooks and sparks debates. Our 136A1 isn't just another in the sky. It's a cosmic outlier that forces humanity to confront the scale and violence of the universe. When we speak of it, we aren't simply describing an object. We're opening the door to understanding how galaxies evolve, how matter recycles through the cosmos, and ultimately, how stars like our own sun came to be. That's why our 136A1 is more than just an astronomical curiosity. It's a reminder of the universe's extremes. The forces at work inside it are so powerful that they defy simple imagination. This star isn't only about raw numbers, its mass, its brightness, its temperature. It's about what those numbers mean for the story of the cosmos. In every way, our 136A1 is a star of superlatives, and diving into its details is like unfolding a cosmic epic written in light and energy. To truly appreciate a 136A1, we need to step back and look at where it lives. The star is not tucked away in some forgotten corner of the cosmos. Instead, it occupies a very special and significant place in our galactic neighborhood. Our 136A1 is located in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Now, the Large Magellanic Cloud, or LMC as astronomers often call it, is not a particularly large galaxy compared to others we've mapped across the universe, but it's one of the most important ones for us because it's relatively close. When we say close in cosmic terms, we're talking about 160,000 light-years away. That might sound impossibly far, but in the grand scale of the universe, where many galaxies are millions or even billions of light-years distant, the LMC is practically in our backyard. The LMC itself is a barred irregular galaxy, which means it doesn't have the neat spiral arms of the Milky Way or the smooth, round shape of an elliptical galaxy. Instead, it looks somewhat ragged and asymmetrical. To the naked eye from Earth, it appears as a faint, cloudy patch in the southern hemisphere's night sky. In fact, it was named after the explorer Ferdinand Magellan, whose crew noticed it during their voyage around the globe in the early 1500s. For observers in the southern skies, the LMC is a constant, ghostly presence, and within it lies one of the most active regions of star formation known to humanity, the Tarantula Nebula. This is where our 136A1 resides. The Tarantula Nebula is a vast stellar nursery, a colossal cloud of gas and dust stretching across more than 1,000 light-years. It's a place where stars are born in staggering numbers, and among its crowded stellar population sits the R136 cluster, the very heart of the nebula. If you could zoom in on this region with a telescope, you'd see a breathtaking tangle of glowing gas, sculpted by the intense radiation and winds from massive stars. This nebula is so energetic that if it were as close to Earth as the Orion Nebula, it would cast visible shadows at night. Right in the core of this energetic stellar nursery lies a 136A1. It doesn't stand alone, it's one of many massive stars in the cluster, but it reigns supreme as the most massive ever observed. Its location is a double-edged sword for astronomers. On one hand, being in the Tarantula Nebula provides us with an incredible opportunity to study a rich population of massive stars in one place. On the other hand, the density of stars, the sheer brightness of the nebula, and the vast amounts of interstellar dust make it difficult to isolate and study any single object in detail. That's one reason why a 136A1 wasn't identified immediately. It took powerful telescopes and detailed analysis to confirm its existence amid the glare of its stellar siblings. But why does its location in the Large Magellanic Cloud matter so much? For one, it's close enough that we can study it in unprecedented detail compared to similar massive stars that might exist farther away. The LMC is essentially a natural laboratory, allowing astronomers to observe how stars form and evolve under slightly different conditions than those in our Milky Way. Its chemical composition, for instance, has lower metallicity, that is, fewer heavy elements, than our galaxy. This lower metallicity affects how stars form, how they shine, and how they die. By observing a 136A1 in this environment, we get crucial insights into how the first stars in the early universe, stars that also had very low metallicity, might have lived and died. The 160,000 light-year distance also gives us perspective. The light from a 136A1 that reaches our telescopes today left the star back when modern humans were just beginning to make their mark on Earth. Think about that. When the first cave paintings were being drawn in Europe, the photons we now capture with advanced observatories were already on their way. This means that when we look at a 136A1, we're seeing it not as it is now, but as it was 160,000 years ago. In cosmic terms, that's not too long ago, but it's still a reminder that astronomy is always a form of time travel. We're never looking at the universe in real time, but always in its past. What makes the LMC particularly interesting is that it's gravitationally interacting with the Milky Way. Over billions of years, this smaller galaxy has been tugged and stretched by our own, and eventually, it's expected that the LMC will merge with the Milky Way entirely. This ongoing interaction stirs up bursts of star formation, feeding regions like the Tarantula Nebula. So, in a sense, our 136A1 is not just a random star. It's a product of galactic dynamics, a creation born from the dance between two galaxies. Its existence is a living record of these cosmic forces at play. When we picture the Large Magellanic Cloud from Earth, we don't see individual stars like a 136A1 with the naked eye. It's just too far away, and the combined light of millions of stars blurs into a misty patch. But when powerful telescopes zoom in, what was once a faint smudge transforms into a spectacular collection of stellar fireworks. The Tarantula Nebula comes alive in shades of pink and purple, sculpted by ultraviolet radiation, while clusters like a 136 burn fiercely at its center. That's the true stage where our 136A1 performs its role, a cosmic theater lit by the brightest and hottest stars known. Understanding its location also helps frame its importance. If a 136A1 were within our own galaxy and just a few thousand light-years away, it would be one of the most dazzling objects in the night sky, easily visible without a telescope. Instead, it sits in this distant satellite galaxy, hidden from casual observation. In some ways, this makes it even more intriguing. It's a treasure we can only glimpse with effort, reminding us of how vast and mysterious the universe really is. Our 136A1 matters because it is not just a star, it is a direct challenge to the boundaries of our scientific knowledge. In astronomy, much of what we know comes from studying patterns. Scientists look at stars of different sizes, ages, and compositions, and from those observations, they create models that explain how stars form, evolve, and die. These models are like carefully constructed maps of the cosmos, guiding us through the vast diversity of stellar life. But every so often, something comes along that doesn't fit neatly into the map. Our 136A1 is one of those anomalies. It pushes right up against the theoretical limits of what we thought possible, and in doing so, it forces astronomers to question, revise, and expand their understanding of how the universe works. Why is this so important? For decades, astrophysicists believed there was an upper limit to how massive a star could be when it formed. That limit was thought to hover around 150 times the mass of our Sun. Beyond that, the pressure of radiation inside the star, the incredible outward force created by the light and energy it produces, was expected to blow away excess material, preventing a star from growing any larger. This made sense in theory, and it fit with the majority of stars we had observed. But then along came a 136A1, with an estimated mass of 200 to 250 suns, far exceeding the supposed ceiling. Its very existence told astronomers, the universe doesn't always play by our rules. That realization alone is enough to make a 136A1 significant, but it's only the beginning. The star matters because it acts like a natural laboratory for extreme physics. Everything about it operates at the outer edge of possibility. Its gravity is staggeringly powerful, its core is burning hydrogen at rates unimaginable compared to ordinary stars, and the energy it radiates into space is millions of times greater than that of our Sun. By studying our 136A1, scientists gain a window into processes that are too extreme to recreate on Earth, even with our most advanced technology. This single star gives us data points about the cosmos that cannot be obtained anywhere else. Another reason astronomers are so fascinated by our 136A1 is the way it helps us understand the origins of stars in the early universe. When the cosmos was young, just a few 100 million years after the Big Bang, conditions were very different from what we see today. Stars that formed back then had little to no heavy elements, and they were thought to grow much larger and more massive than the stars forming in our galaxy today. But we can't directly observe those ancient giants. They burned out billions of years ago. What we can do is study stars like a 136A1, which live in environments with relatively low amounts of heavy elements, like the Large Magellanic Cloud. In other words, our 136A1 is a living analog for the first stars in the universe. By observing it, we get clues about how those long-dead titans lived and died, and how they seeded the cosmos with the elements necessary for life. There's also the matter of what a 136A1 represents in terms of cosmic influence. Stars like our Sun are important, of course, but they live quiet, steady lives. Massive stars like our 136A1, however, are like fireworks. They burn incredibly hot and fast, and when they die, they do so in spectacular explosions. These explosions scatter heavy elements across their galaxies, elements that eventually become the building blocks for planets, oceans, and even living creatures. Without massive stars like a 136A1, the universe would be a much duller, emptier place. That means studying this star is not just about curiosity, it's about tracing our own cosmic origins. Our 136A1 also fascinates astronomers because it challenges our expectations about stellar stability. Stars this massive are not supposed to last very long. The tremendous forces inside them create instability, and they lose mass through ferocious stellar winds at an astonishing pace. By observing a 136A1's current state, scientists can learn about the delicate balance of forces inside it. Gravity pulling inward, radiation pushing outward, nuclear fusion fueling the whole process, and how close it comes to collapsing or exploding. It's a real-time experiment in stellar physics, one that tests our theories about how matter and energy behave under the most extreme conditions. Beyond the science, there's something deeply human about why our 136A1 matters. For thousands of years, people have looked up at the stars and wondered about their nature. Each time we've learned something new, whether it was Galileo discovering moons around Jupiter or Hubble revealing the expansion of the universe, it has expanded not just our scientific understanding, but our sense of place in the cosmos. Our 136A1 does the same. It reminds us that the universe is still full of surprises. Even with our advanced telescopes, powerful computers, and elaborate theories, we are still students, humbled by the enormity and complexity of creation. It's also worth noting the inspiration factor. Stars like a 136A1 capture the imagination of both scientists and the public. They embody extremes, size, brightness, temperature, that go beyond ordinary comprehension. When people hear that a single star can be hundreds of times more massive than the Sun and millions of times brighter, it evokes a sense of awe. It's a reminder that the universe is not only vast but filled with wonders that dwarf anything we know on Earth. This sense of awe fuels curiosity, and curiosity drives discovery. In that way, our 136A1 matters not only for science but also for culture, for the way it shapes our collective imagination about the cosmos. Finally, our 136A1 is a kind of benchmark. When astronomers study stars elsewhere in the universe, whether in distant galaxies or in theoretical models, they often compare them to the most extreme examples we've already identified. R136a1 serves as a measuring stick for what's possible. If another star is discovered that seems even more massive, astronomers will ask, is it more extreme than R136a1? Or does it redefine the upper boundary once again? In that sense, this star is not just an object, it's a frontier, a moving edge of knowledge that challenges us to keep pushing further. So when we ask why R136a1 matters, the answer comes on multiple levels. It matters because it defies the theoretical limits of stellar formation. It matters because it gives us a living glimpse of the earliest stars in the universe. It matters because its existence helps explain how galaxies evolve, how elements are forged, and ultimately, how life can arise. And perhaps most importantly, it matters because it humbles us, reminding humanity that for all our progress, the universe still has mysteries waiting to be unraveled. The story of how R136a1 was first discovered is a fascinating tale that blends cutting-edge technology, the persistence of astronomers, and the gradual unveiling of the cosmos' deepest secrets. For a long time, the heart of the Tarantula Nebula, where R136a1 resides, was thought to be something very different from what it actually is. Early ground-based observations in the mid-20th century showed a bright, concentrated glow at the center of the nebula. To many astronomers at the time, this light resembled a single, supermassive star, so luminous that it seemed almost impossible. Some even speculated that it might not be a star at all, but perhaps a new kind of celestial object, one that defied conventional stellar physics. The challenge was that the Tarantula Nebula is incredibly crowded. Its central region, where the R136 cluster lies, is packed with some of the brightest and hottest stars in the entire local universe. From Earth, even through powerful telescopes of the time, the light of these stars blended together into what looked like a single, dazzling point. This was the first big obstacle, distinguishing individual stars in such a densely packed environment. For decades, this unresolved blob of light was a source of both mystery and debate. It wasn't until the 1980s that breakthroughs finally began to happen. On the ground, astronomers used some of the largest telescopes available, equipped with advanced imaging and spectroscopy techniques, to try and tease apart the light. Spectroscopy is particularly important here because it allows scientists to spread out the light from a source into its spectrum, like a cosmic fingerprint, and then study the features that reveal the temperature, composition, and motion of the object. By examining the spectrum, astronomers started to realize that what they were looking at wasn't just a single star but a cluster of very massive, very young stars packed tightly together. This is where the R136 cluster got its name, and within it, R136a1 emerged as one of the brightest and most massive members. But even then, the resolution of ground-based telescopes wasn't quite enough to give a clear, unambiguous picture. The real breakthrough came with the launch of the Hubble Space Telescope in 1990. Hubble's vantage point above Earth's atmosphere allowed it to avoid the blurring effects of atmospheric turbulence, giving it a sharpness that ground-based telescopes of that era simply could not match. When astronomers pointed Hubble's instruments toward the Tarantula Nebula, what had once been a fuzzy glow resolved into a spectacular swarm of individual stars. Suddenly, the veil was lifted, and R136a1 could be seen clearly for what it was, not just a single blur, but a distinct, unbelievably massive star shining among its equally colossal siblings. The observations from Hubble confirmed what astronomers had begun to suspect, that this was not some mysterious, exotic object, but rather the most massive star yet identified. In the following years, data from Hubble combined with high-resolution spectroscopy from ground-based observatories allowed scientists to pin down R136a1's extraordinary characteristics. Its mass far above the 150 solar mass theoretical limit, its blinding luminosity millions of times greater than the Sun, and its extreme temperature. It's important to emphasize how revolutionary this discovery was. Before Hubble, the R136 cluster was often referred to as a single superstar, one object of unimaginable size. But with Hubble's clarity, the superstar was revealed to be a tightly bound cluster of massive stars, each one enormous in its own right. R136a1 stood out as the heavyweight among them, pushing our understanding of stellar physics further than ever before. This transformation, from the idea of one impossible object to the reality of a cluster of incredible but physically plausible stars, marked a turning point in astronomy. It showed how vital improved observational tools are for uncovering the truth about the universe. Without Hubble, R136a1 might have remained an enigma for decades longer, its light forever blurred into the crowd. But Hubble wasn't the end of the story. As technology advanced, new instruments on Earth also contributed to our understanding. The development of adaptive optic systems, technology that uses deformable mirrors to correct for the distortion of Earth's atmosphere in real time, gave ground-based telescopes an almost Hubble-like sharpness. Facilities like the Very Large Telescope, VLT, in Chile provided even more detailed observations of a 136A1 and its cluster. These instruments help confirm not only the star's mass and luminosity but also its classification as a Wolf-Rayet star, shedding mass through ferocious stellar winds. The discovery of a 136A1 was not a single aha moment but rather a gradual unveiling. First came the suspicion that the bright glow in the Tarantula Nebula wasn't a single star. Then came the careful spectroscopic work that suggested multiple massive stars were hiding there. Finally, Hubble and advanced ground-based instruments peeled back the last layer of mystery, showing us the true nature of a 136A1. Each step built upon the last, a perfect example of how science progresses, slowly, methodically, and with each new tool sharpening the picture. For the astronomers who first studied a 136A1, the discovery was nothing short of exhilarating. Here was a star that shouldn't exist according to the models, a star that forced them to go back to the drawing board and rethink the limits of nature. And for the wider scientific community, it was a reminder that even in regions we thought we understood, the universe still held surprises waiting to be revealed. Even today, the story of a 136A1's discovery is a cautionary tale about assumptions in science. For decades, people believed the central object in the Tarantula Nebula might be a singular supermassive star, something completely outside the framework of stellar physics. It took better data to reveal that the truth, while still extraordinary, fit within the broader context of star formation, albeit at the very extreme edge. The discovery underscores a powerful lesson. The universe often looks stranger or more impossible than it really is, until we have the right tools to see it clearly. To understand our 136A1 fully, it's not enough to look at it in isolation. This star, extraordinary as it is, does not live alone in the cosmos. It resides at the very heart of one of the most spectacular stellar gatherings in the local universe, the R136 cluster. If R136A1 is the heavyweight champion of stars, then R136 is the Colosseum where titans are born, shine, and eventually burn themselves out in breathtaking fashion. The cluster provides the context, the stage, and the environment that made a 136A1 possible in the first place. The R136 cluster is located at the very core of the Tarantula Nebula within the Large Magellanic Cloud, about 160,000 light-years from Earth. This nebula is often called a stellar nursery because it is bursting with activity, churning out new stars at an incredible rate. The cluster itself is relatively young by cosmic standards, only a few million years old. That might sound ancient to us, but in terms of stellar lifetimes, it's barely out of the cradle. Our Sun, by comparison, is about 4.6 billion years old. That means a 136 and its residents are newborns on the galactic stage, blazing with the furious energy of youth. What makes a 136 so remarkable is not just its age but its population. It contains some of the most massive and luminous stars ever observed. In fact, astronomers have catalogued dozens of stars within this cluster that exceed 50 times the mass of the Sun, and several that surpass 100 solar masses. To put that in perspective, stars more than 20 or 30 times the mass of the Sun are already considered rare giants. Yet here, in one tightly packed region, is an entire swarm of these colossal objects. Our 136A1 is the most massive among them, but it is far from alone in its greatness. It is surrounded by siblings that, anywhere else in the galaxy, would each command attention as extraordinary stars in their own right. From Earth, seeing into the R136 cluster is no easy task. The sheer density of stars, combined with the glowing clouds of gas and dust in the Tarantula Nebula, makes it challenging to separate one star from another. Before high-resolution imaging from the Hubble Space Telescope and ground-based telescopes equipped with adaptive optics, the cluster's light appeared as a single brilliant point. Only when astronomers were able to resolve it did the true scale of the cluster become clear, a dazzling swarm of hot, blue-white stars crammed into a space only a few light-years across. The physical environment inside a 136 is almost unimaginable. Stars like a 136A1 pour out intense radiation and stellar winds, streams of charged particles moving at thousands of kilometers per second. In a typical neighborhood of stars, like our Sun's, such winds and radiation would be powerful enough to dominate the local environment. But in our 136, nearly every star is a powerhouse. The combined energy output of the cluster is so enormous that it ionizes the surrounding hydrogen gas in the Tarantula Nebula, causing it to glow vividly in ultraviolet and visible light. This is why the Tarantula is one of the brightest emission nebulae known, and why it looks so dramatic in telescope images. What's more, the close quarters of a 136 mean that its stars can interact with one another in ways that stars in more sparsely populated regions cannot. Gravitational interactions, collisions of stellar winds, and even the possibility of stars merging all become more likely in such an environment. Some scientists believe that the extraordinary mass of a 136A1 might, at least in part, be explained by such dynamics. It's possible that in the dense crush of a 136's core, smaller massive stars collided or merged, producing the ultramassive giant we see today. If true, a 136A1 would not only represent the upper limits of natural star formation but also the chaotic, violent outcomes of life in such a stellar metropolis. The cluster is also a preview of the cosmic fireworks to come. Massive stars live fast and die young, and a 136 is packed with them. Within a few million years, many of its residents will explode as supernovae or hypernovae, leaving behind neutron stars or black holes. These explosions will send shockwaves through the surrounding nebula, compressing gas and possibly triggering new waves of star formation. In this way, our 136 isn't just a cluster of stars, it's a machine for galactic evolution, recycling material and reshaping its environment on a massive scale. The death of its most massive members will enrich the surrounding galaxy with heavy elements like oxygen, carbon, and iron, the very ingredients needed for planets, oceans, and life. To put it into perspective, think about how different our Sun's neighborhood is. The closest star to us, Proxima Centauri, is over 4 light-years away. In contrast, in the core of our 136, stars are packed together with separations measured in tenths of a light-year, sometimes even less. If our Sun were transplanted into this environment, the night sky would not be sprinkled with faint dots but ablaze with dazzling blue stars shining so brightly they would cast shadows on the ground. The sheer energy of that environment would make Earth an unrecognizable place, bathed constantly in ultraviolet radiation far stronger than anything we experience. Our 136A1 is thus not an isolated marvel but a part of a grander cosmic symphony. Its existence is tied to the cluster's extreme conditions, which both fostered its birth and continue to shape its evolution. Without the density, the raw material, and the dynamism of a 136, it's unlikely a star like a 136A1 could have formed at all. This makes the cluster context essential to understanding why this star exists in the first place. It's not just about the star, it's about the environment that enabled such an outlier to come into being. And while a 136A1 stands as the most massive star we've found, it also raises an intriguing possibility. Could there be others in the cluster, perhaps hidden by dust or blended light, that rival or even surpass it? The crowded conditions make it difficult to say for sure. As telescopes like the James Webb Space Telescope continue to peer into the cluster, we may yet find that a 136A1 is not alone even in its extreme supremacy. The cluster is a reminder that the universe rarely gives us just one spectacular object. It often gives us entire regions bursting with wonders. In short, our 136 is the cosmic nursery that makes sense of our 136A1's existence. It is both the cradle and the proving ground for massive stars, and it gives astronomers a unique opportunity to study a whole population of stellar giants at once. The cluster shows us what happens when nature turns up the dial on star formation to its maximum setting, and a 136A1 is the brightest, most massive jewel in that crown. When we talk about the mass of our 136A1, we are truly entering the territory of extremes. Mass is one of the most fundamental characteristics of a star. It determines everything about its life, how hot it burns, how long it lives, and how it will eventually die. For ordinary stars like our Sun, mass sets the pace of a slow, steady existence. But for our 136A1, mass is not just a number. It is the defining feature that makes this star so extraordinary, so rare, and so scientifically valuable. Estimates put its mass at around 200 to 250 times that of our Sun, making it the most massive star we've ever confirmed in the observable universe. To put this in perspective, let's start with the familiar. Our Sun, with its mass of about 2 × 10 cubed kilograms, is the standard yardstick for measuring stellar mass. It is a middleweight star, neither the smallest nor the largest, but comfortably stable and long-lived. Most stars in the universe are actually smaller than the Sun. Red dwarfs, which make up the vast majority of stars, can be as little as 8% the Sun's mass. On the other side of the scale, the largest normal stars we encounter are usually 50 or 100 times the mass of the Sun. Already, those are colossal giants compared to what we know here at home. But a 136A1 is something else entirely. It tips the scale at more than 200 suns. That figure is astonishing because it defies earlier scientific consensus. For decades, astrophysicists thought that stars could not exceed about 150 solar masses. The reasoning behind this upper mass limit was straightforward. As a star grows more massive, the amount of radiation it produces increases exponentially. At some point, the pressure of this radiation should become so intense that it literally blows away any additional material trying to fall in, preventing the star from growing larger. This is what made a 136A1 such a shocking discovery. It didn't just break the rules, it smashed through them. At 200 to 250 times the mass of the Sun, our 136A1 sits far above that supposed limit. How is this possible? There are a few explanations scientists consider. One is that our earlier models were simply too simplistic, and the physics of radiation pressure, accretion, and stellar winds are more complex than we thought. Another possibility is that a 136A1 didn't form in the usual way. Instead of accreting material slowly from a gas cloud, it may have grown through mergers of multiple smaller massive stars inside the dense core of the R136 cluster. In an environment where stars are packed so close together, collisions and mergers aren't just possible, they may be inevitable. If 2 or more massive stars collided, their combined mass could create an ultramassive star like a 136A1. The difference between the Sun's mass and our 136A1s is almost impossible to visualize. Imagine placing 200 suns side by side. That's the equivalent weight of this single star. Or, put another way, our 136A1 contains more mass than the combined total of many stellar systems in our galactic neighborhood. And yet, all of this mass is squeezed into a radius only about 30 to 40 times larger than the Sun's. That means the density and gravitational pull at its core are beyond anything we can directly imagine. The sheer gravitational compression produces temperatures and pressures that drive nuclear fusion at rates millions of times faster than in our Sun's core. This tremendous mass has profound consequences for the star's life. For one thing, it makes a 136A1 wildly unstable. The more massive a star is, the shorter its lifespan. Our Sun, with its moderate mass, will shine steadily for about 10 billion years. Our 136A1, by contrast, will likely last only 2 to 3 million years before burning out. In fact, given that it already appears to be several million years old, it may be well along the path to its eventual explosive end. Its mass, the very thing that makes it extraordinary, is also the reason it is doomed to a brief existence. Another consequence of this extreme mass is how it interacts with its environment. Stars like a 136A1 don't simply sit quietly in space, they reshape everything around them. Their immense gravitational pull gathers and compresses nearby material, while their fierce stellar winds push other material away. In the crowded core of the R136 cluster, this interplay creates a chaotic, turbulent environment where gas is constantly being sculpted, compressed, and blown apart. The mass of our 136A1 is thus not just a personal characteristic, it's a cosmic influence, altering the very fabric of its stellar nursery. The discovery of a star this massive also changes how we think about the upper boundaries of star formation. If our 136A1 exists at 200 to 250 solar masses, might there be stars even larger? Is this the true upper limit, or just the largest we've observed so far? Astronomers are cautious about drawing conclusions, but the very existence of a 136A1 opens the door to the possibility of even more massive stars hiding in distant galaxies. If telescopes like the James Webb Space Telescope find other giants like it, or bigger still, it could rewrite entire sections of astrophysics textbooks. It's also worth contrasting our 136A1's mass with some of the other record-holding stars. For example, UY Scuti, often described as the largest star by radius, has a volume that could swallow thousands of suns, but its mass is only about 30 times greater than the Sun's. Betelgeuse, the famous red supergiant, has a similarly large radius but is not exceptionally massive by comparison. What makes a 136A1 unique is that its defining feature is not its sheer size but the staggering amount of material packed into its core. In terms of mass, no other confirmed star comes close. Finally, there's the philosophical side of this discussion. To say that a star weighs 200 to 250 times as much as the Sun is to throw out a number so large that it almost loses meaning. But what it really tells us is that nature has the capacity to create extremes far beyond the everyday scale of our solar system. The Sun feels massive to us. It contains 99.8% of all the mass in the solar system. Yet here is a single star that outweighs it 200 times over. This forces us to rethink what big and small even mean on the cosmic stage. Our 136A1 isn't just big, it's proof that the universe is willing to stretch the boundaries of what we once thought impossible. When we talk about the brightness of our 136A1, we are entering into a scale of luminosity that boggles the human mind. To say that this star is luminous doesn't do it justice. It is not just bright, it is a cosmic beacon, shining with the radiance of millions of suns combined. In fact, estimates suggest that a 136A1 is somewhere between 8 million and 10 million times more luminous than our Sun, numbers like that are almost impossible to truly imagine. But breaking them down helps us understand just how extraordinary this star really is. Let's begin with a baseline, our Sun. The Sun is bright enough that it dominates life on Earth, delivering light and energy across 150 million kilometers of space to warm our planet, drive our climate, and sustain all living organisms. The total power output of the Sun, its luminosity, is about 3.8 times 10 squared watts. In practical terms, that's enough energy every second to power civilization on Earth for millions of years. To us, the Sun feels overwhelming in its power, and yet compared to a 136A1, it is a flickering candle in the distance. Now, take that luminosity and multiply it by 10 million. That's what a 136A1 is pumping into space every single second. In energy terms, we're talking about 3.8 times 10 cubed watts of radiant power. This number is so large it surpasses comprehension. It is 1 trillion times greater than the total energy output of human civilization across all of recorded history, every second. Our 136A1 is essentially a cosmic engine, blasting energy into its surroundings at a rate that reshapes everything nearby. But brightness is not just about numbers, it's about consequences. Such extreme luminosity means that a 136A1 is one of the most dominant stars in its cluster. The radiation it emits is powerful enough to ionize vast regions of gas around it, contributing to the glowing beauty of the Tarantula Nebula. This intense radiation also sculpts the environment, blowing away dust, heating surrounding clouds, and even preventing some regions from collapsing to form new stars. In essence, a 136A1 is so bright that it actively controls the life cycle of the nebula around it, deciding where stars can and cannot be born. It's also important to remember that a 136A1's luminosity is not just ordinary visible light like what we see from the Sun. Much of its output comes in the form of ultraviolet radiation, which is far more energetic. If a 136A1 were magically transported to the position of our Sun in the solar system, Earth would be blasted sterile in an instant. The ultraviolet radiation would strip away our atmosphere and boil our oceans. At such close range, the star's light would be so powerful that no human eye could look at it, even indirectly, without being destroyed. Our planet simply couldn't exist in the glare of such a luminous monster. This raises another fascinating point. Despite its unbelievable brightness, a 136A1 is invisible to the naked eye from Earth. Why? Because of distance. At 160,000 light-years away, even a star that is 10 million times brighter than the Sun fades into obscurity when viewed across such vast cosmic distances. To us, without a telescope, the light from a 136A1 is drowned out by the collective glow of the Tarantula Nebula. This creates a strange paradox. One of the brightest stars in existence is hidden from human sight, a giant blazing in darkness. The sheer luminosity of our 136A1 also has dramatic implications for its stability. Light is not just illumination, it exerts pressure. Every photon streaming out from the star carries momentum, and when trillions upon trillions of photons pour outward every second, their combined pressure is immense. This radiation pressure pushes against the star's own gravity, creating a constant tug-of-war. In smaller stars, gravity easily wins. But in our 136A1, the battle is finely balanced. The star is so luminous that the radiation pressure nearly blows it apart from within. In fact, this is one of the reasons astrophysicists once thought stars above 150 solar masses couldn't exist, because the brightness alone should make them unstable. Our 136A1 defies this expectation, somehow holding itself together, though at a great cost. It sheds mass at an incredible rate through stellar winds driven by that very same radiation. Now let's put this luminosity into a more human frame of reference. Imagine standing on a hypothetical planet orbiting our 136A1 at the same distance Earth orbits the Sun. The amount of light and energy hitting that planet would be 10 million times greater than what Earth receives. The surface would not only be uninhabitable, it would likely vaporize entirely. To orbit safely, a planet would need to be billions of kilometers away, far beyond Pluto's orbit. And even at those distances, the glare of our 136A1 would dominate the sky. Its brilliance would make it appear hundreds of times brighter than a full moon. This is what we mean when we call it luminous. It is not just a star, but a star so powerful it could redefine the concept of daylight for an entire solar system. Astronomers measure stellar luminosity in magnitudes, a logarithmic scale where each step represents a factor of brightness. On this scale, our 136A1 is astonishingly extreme. Its absolute magnitude in the visible spectrum is around -12, compared to the Sun's +4.8. That means it is billions of times more radiant in visible light alone. To compare, the full moon has an absolute magnitude of about -12.7, meaning a 136A1's brightness, if it were at the same distance as the Sun, would rival the moon's glow in our sky, but it would be constant, blinding daylight. Another fascinating consequence of our 136A1's luminosity is how it affects its lifespan. A star shines by converting mass into energy through nuclear fusion. The brighter the star, the faster it burns through its nuclear fuel. Our Sun burns steadily, consuming only about 4 million tons of hydrogen every second, yet it has enough fuel to last 10 billion years. Our 136A1, by contrast, burns its fuel at a rate so high that its lifespan is measured not in billions, but in just a few million years. It's like comparing a campfire to a rocket engine. Both produce heat and light, but one burns slowly and steadily, while the other unleashes its energy all at once in a brilliant but fleeting blaze. This immense brightness is also why our 136A1 is classified as a Wolf-Rayet star. Such stars are characterized by their extreme luminosities, high temperatures, and the fact that they are losing mass at furious rates. The stellar winds driven by its light carry away millions of times more material each year than the Sun loses in the same period. Essentially, our 136A1 is so bright that it is destroying itself, one layer at a time, peeling away its outer envelopes as radiation pressure tears at its surface. In summary, the luminosity of our 136A1 is one of the defining aspects of its character. At millions of times brighter than the Sun, it stands as one of the most radiant objects known to science. Its brilliance is not just a statistic, it's a force that shapes its environment, dictates its lifespan, and challenges our understanding of stellar stability. It is light not just as illumination, but as power, as destruction, as creation. And it reminds us that the universe operates on scales of energy and brightness so vast that human comparison often falls short. When we shift our attention from the mass and luminosity of a 136A1 to its radius, we find another layer of wonder, but also an important clarification. Unlike stars such as UY Scuti or Betelgeuse, which are famous for their colossal volumes, our 136A1 does not owe its legendary reputation to its sheer size in space. Instead, its claim to fame lies in its density of power, its incredible mass packed into a comparatively modest volume. Estimates suggest that a 136A1's radius is roughly 30 to 40 times that of our Sun. That is still enormous, truly gigantic compared to what we know on Earth, but when set beside its breathtaking mass and luminosity, it reveals a star that is defined less by how big it looks and more by how extreme it is on the inside. Let's build this comparison carefully. Our Sun has a radius of about 696,000 kilometers. If you could scale it down to the size of a basketball, Earth would be the size of a small bead orbiting about 25 meters away. Now, take that sun and expand it 30 to 40 times in every direction. That gives you our 136A1. Its radius falls somewhere between 20 and 28 million kilometers. To put this into perspective, if you placed a 136A1 at the center of our solar system where the Sun is, its surface would extend well past the orbit of Mercury, and possibly close to the orbit of Venus. Earth, thankfully, would remain outside of the star's surface, but the radiation pouring from it would erase our planet instantly. Even so, 30 to 40 solar radii is not the largest star size by far. Scuti, a red supergiant, has a radius nearly 1,700 times that of the Sun Betelgeuse. Another red supergiant expands to about 900 solar radii. Compared to these swollen behemoths, our 136A1 is actually relatively compact. That's why astronomers emphasize that a 136A1's extreme nature isn't about size. It's about mass, density, and energy output. Think of it as the difference between a soap bubble and a diamond. One can be huge but fragile, while the other is smaller but far denser and more powerful. Our 136A1 is the diamond of the stellar world, not the balloon. Its radius also speaks volumes about its temperature and energy. Stars that are cooler, like red giants, expand to enormous radii but glow with a gentler red light. Stars like our 136A1, however, are blazing hot, about 50,000 Kelvin at their surface. This incredible heat means the star does not need to be as large as a red giant to shine so brilliantly. Instead, its smaller but incredibly dense surface pumps out more energy per square centimeter than almost any other known star. It is a compact furnace, shining with a ferocity that larger, puffier stars simply cannot match. Another way to think of its radius is in terms of volume. A sphere 30 to 40 times the radius of the Sun translates into about 30,000 to 60,000 times the Sun's volume. That might sound huge, and it is, but remember, the mass of our 136A1 is more than 200 suns. This means its density, while still less than water, stars are mostly gas and plasma, is far greater than that of the Sun when averaged across its entire volume. It's this density of mass within a relatively moderate radius that creates the extreme gravitational pressure at the core, fueling the ferocious rate of fusion that makes a 136A1 shine millions of times brighter than our Sun. To visualize this, imagine if you had 200 suns and you tried to squeeze them into a volume only 30,000 to 60,000 times the Sun's size. That balance produces unimaginable pressures in the core, pressures that drive nuclear fusion at speeds and intensities far beyond anything we see in normal stars. The radius, in this sense, is not just a measurement of size. It's a clue about the extraordinary internal forces that keep the star burning. It's also worth noting that our 136A1's radius is not fixed. Like all massive stars, it will evolve as it ages. Right now, it exists in its hot, luminous, massive phase, but eventually, as it sheds mass through stellar winds and burns through its hydrogen, its radius will change. It may swell as it transitions into later evolutionary stages, though because of its incredible mass, its exact fate is uncertain. Unlike red supergiants, which expand to enormous sizes before exploding, our 136A1 may lose so much material through radiation-driven winds that it doesn't balloon to quite the same scale. Instead, it may remain comparatively compact until its violent end, collapsing directly into a black hole or detonating in a hypernova. This raises another fascinating contrast. The human imagination often equates biggest with best or most extreme. Scuti is often celebrated as the largest star because of its radius. But while Scuti might occupy the largest volume, its mass is relatively modest, only 30 suns, compared to our 136A1's 200 to 250. Our 136A1 shows us that size and mass are not the same thing, and that the most extreme stars are not necessarily the ones that take up the most space. Instead, they are the ones that pack the greatest amount of matter and energy into their cores. The radius of our 136A1 also plays a role in how it interacts with its cluster environment. A radius of 30 to 40 suns might sound huge, but in the crowded conditions of the R136 cluster, stars are packed so tightly that their outer atmospheres and stellar winds can interact. A larger radius would make collisions or mass transfers more likely, but a 136A1's relatively compact form means it can remain somewhat self-contained, even while blasting out torrents of material. Still, its winds are strong enough to affect its neighbors, stripping gas from the nebula and helping to carve out the glowing cavities we see in images of the Tarantula Nebula. One way to make this more tangible is to compare it to everyday scales. If our Sun were the size of a basketball, our 136A1 would be a sphere about the size of a small car. That might not sound huge at first, until you remember that within that car is packed more than 200 times the mass of the basketball. And that car isn't made of steel or rubber, it's a roaring ball of plasma, its surface hotter than almost any other star, blasting energy into space at a rate no human instrument could replicate. In essence, a 136A1's radius illustrates a vital truth. Its greatness is not in being the widest star, but in being the most massive star squeezed into a form that burns with unrivaled intensity. Its 30 to 40 solar radii put it in a middle ground, larger than most stars in the universe, but dwarfed in sheer size by the puffed-up red supergiants. Yet those red giants, for all their size, lack the staggering density, mass, and ferocity of a 136A1. That's why astronomers emphasize its mass and luminosity over its radius. The star's size is impressive, but its compact enormity, the fact that so much is contained in so relatively little space, is what makes it extraordinary. When we turn to the question of energy output, we come face to face with one of the most awe-inspiring truths about a 136A1. It is an engine of almost unimaginable power, blazing with an energy output that makes our Sun look like a dim campfire beside a raging supernova. To grasp the scale, we have to start with what we know, the Sun, and then climb step by step into the uncharted heights of a 136A1's brilliance. Our Sun, steady and reliable, releases about 3.8 times 10 squared watts of power every second. That's a 3 followed by 26 zeros, a number so enormous that if you tried to write it in full, it would spill off the page. Every one of those watts is a joule of energy released each second, and that output powers everything we know: the warmth on your skin, the cycles of climate, the growth of forests, the sparkle of oceans. For us, the Sun is overwhelming. If you've ever felt its heat on a summer day or seen the way its light floods the Earth, you've experienced firsthand the immense power of those 3.8 times 10 squared watts streaming across space. Now imagine multiplying that by 8 million to 10 million. That is the range of luminosity astronomers estimate for our 136A1. In other words, this single star emits around 3 times 10 cubed watts of energy every second. To put it into words, that's a million trillion watts pouring into space continuously, without pause, for millions of years. Numbers like these are not just difficult, they're nearly impossible for the human brain to conceptualize. But let's try. If the entire energy output of the Sun in 1 second could somehow be captured and stored, it could power Earth's entire civilization at today's energy usage for roughly 7 million years. Now consider our 136A1. In that same 1 second, it releases as much energy as our Sun would in 10 million seconds, over 115 days. Every heartbeat of our 136A1 floods the universe with more light and energy than our Sun will release in months. But the story doesn't stop there. Because this energy is not spread evenly across the electromagnetic spectrum. A huge fraction of a 136A1's output comes as ultraviolet radiation, which is far more energetic than the visible light we're familiar with. Ultraviolet photons carry enough punch to rip electrons off atoms, ionizing gas across vast regions of space. That's why the Tarantula Nebula glows so spectacularly in images taken by telescopes. Our 136A1 and its neighboring giants are bombarding the gas with ultraviolet light, stripping electrons, and causing the atoms to re-radiate in dazzling colors. Essentially, the nebula is a giant glowing cloud because a 136A1's energy floods it like a cosmic floodlight. Let's also think about the raw physical consequences of that output. Each second, the photons rushing out of our 136A1 crash into the surrounding material, heating it to thousands of degrees. The energy is so intense that it generates stellar winds, streams of particles hurled outward at thousands of kilometers per second. These winds carry away not just light but actual matter, peeling off the outer layers of the star and dumping them into the surrounding environment. That mass loss is powered entirely by energy, and the winds themselves carry as much as 10 billion times the mass the Sun loses each year. It is a star quite literally blowing itself apart with its own brilliance. Another way to contextualize this is to consider Earth. If a 136A1 were magically swapped with our Sun, Earth would be incinerated in an instant, not just burned, but obliterated by radiation. The sheer torrent of energy would vaporize the atmosphere within moments, boil the oceans into space, and melt the crust of the planet. In fact, you wouldn't need to be at Earth's distance to suffer destruction. Any hypothetical planet within several tens of astronomical units, billions of kilometers, would be uninhabitable. Life as we know it could not survive anywhere near such an inferno. The energy output also determines the star's lifespan. Stars shine by converting mass into energy through nuclear fusion, in which hydrogen nuclei merge to form helium. For every kilogram of hydrogen fused, about 0.7% of its mass is converted directly into energy, thanks to Einstein's famous equation, E=mc². The Sun consumes around 4 million tons of hydrogen per second, and that's what fuels its 10 billion year life. But for our 136A1, the numbers are staggering. To produce its enormous luminosity, it must be burning through hundreds of millions of tons of hydrogen every second. The result is that it will exhaust its supply in just a few million years, a cosmic blink of an eye. Energy, in this case, is both a gift and a curse. It makes a 136A1 extraordinary, but it dooms it to a short and violent life. One way astronomers describe the energy output of such stars is in terms of solar luminosities, how many times brighter they are than the Sun. For our 136A1, that number is up to 10 million solar luminosities. If you were to place a 136A1 at the same distance as our Sun, it would shine in the sky not just as a dazzling star, but as an overwhelming, searing light brighter than the full moon by a factor of hundreds of thousands. Day and night would no longer exist, the entire sky would blaze with an unending radiance. The consequences extend even further. Such enormous energy output produces radiation pressure, which is one of the fundamental challenges for massive stars. Radiation pressure is the force exerted by photons when they collide with matter. In smaller stars, gravity easily keeps matter bound despite the outward push of light. But in our 136A1, the outward pressure from light is almost as strong as the inward pull of gravity. This delicate balance is why the star loses mass so rapidly, and why its continued existence seems to defy the limits predicted by theory. Without this energy, the star would be stable. But with it, it lives on the razor's edge of stability, constantly at risk of tearing itself apart. Perhaps the most poetic way to think of a 136A1's energy output is this. It is not just light, but the raw transformation of matter into power. Every second, countless tons of hydrogen vanish, turned into helium and energy, and hurled outward into the cosmos. The light from a 136A1 that we see today began its journey 160,000 years ago, before modern humans even existed, and it has been shining like this for millions of years before that. That relentless stream of power has been shaping the Tarantula Nebula, carving out its vast cavities, and seeding the environment for future stars. And yet, for all this brilliance, our 136A1 is just one star. Across the universe, there are billions of stars, each pouring out their own energy. But even in that vast company, our 136A1 is rare, a singular furnace at the edge of what is possible. Its energy output isn't just impressive, it is a cosmic record, a demonstration of nature's ability to stretch the limits of physics to extremes we can barely comprehend. When it comes to visibility, our 136A1 presents us with one of the greatest paradoxes in all of astronomy. Here is a star that burns with a luminosity millions of times greater than the Sun, a star so powerful that it redefines the upper limits of stellar mass and energy output, and yet you and I cannot step outside at night, look up at the sky, and see it. To the naked eye, our 136A1 is invisible. For a star that blazes like a cosmic furnace, this fact seems counterintuitive, even frustrating. How can something so luminous be hidden from us? The answer lies in two critical factors: distance and dust. Let's begin with distance. Our 136A1 resides in the Large Magellanic Cloud, LMC, a satellite galaxy orbiting the Milky Way, located about 160,000 light-years away. To put that into perspective, the nearest star to us, Proxima Centauri, is only 4.24 light-years away. The Sun's closest bright neighbor, Sirius, sits at 8.6 light-years. Betelgeuse, the famous red supergiant in Orion, lies around 642 light-years away. Already at that distance, Betelgeuse, despite being around 100,000 times brighter than the Sun, appears only as a twinkling point in our night sky. Now scale that out to our 136A1. It is 250 times farther away than Betelgeuse. Even with its incredible brightness, that vast gulf of space dims its light to the point that it blends into the general glow of its environment, beyond the reach of unaided human vision. The math of brightness and distance makes this clearer. Apparent magnitude is how astronomers measure how bright an object looks from Earth. Our 136A1's absolute magnitude, its true brightness at a standard distance, is about -12, which is brighter than nearly anything else in the galaxy. But from 160,000 light-years away, its apparent magnitude drops to about +12 or +13. For context, the faintest star most humans can see without telescopes under perfect dark sky conditions is around magnitude +6. That means our 136A1 is roughly 100 times too faint to be seen by the naked eye. You could stare at the Tarantula Nebula for hours from a mountaintop with crystal-clear skies and never glimpse it directly. But distance is only half the story. The other factor is dust. Our 136A1 lies not in empty space, but deep within the Tarantula Nebula, a swirling star-forming region filled with thick clouds of gas and interstellar dust. Dust is notorious for scattering and absorbing visible light, particularly in the shorter wavelengths like blue and ultraviolet. Since our 136A1 radiates most of its energy in the ultraviolet part of the spectrum, much of that light never reaches us directly. It is absorbed and re-emitted by the surrounding nebula. What we actually see, when we look toward the Tarantula Nebula, is not the raw light of a 136A1 but the glowing response of the nebula itself, lit up like a lantern by the star's radiation. The nebula steals the spotlight, while the star that powers it hides behind the curtain. This makes our 136A1 a kind of cosmic paradox. It is so bright that it shapes and illuminates its environment across light-years of space, yet so hidden that no human eye has ever truly seen it. Only with telescopes, which can collect faint light over long exposures and peer through the interference of dust, can astronomers isolate a 136A1's glow from the chaotic background of its cluster. The Hubble Space Telescope, for example, has given us direct images of the R136 cluster, showing the crowded field of massive stars with a 136A1 standing out as the heavyweight among them. Instruments sensitive to ultraviolet and infrared light, such as those aboard Hubble and the James Webb Space Telescope, are especially crucial because they can pick up the radiation that dust either blocks or re-radiates. Without them, our 136A1 would remain a mystery. It's worth reflecting here on how extraordinary this is. Imagine a star so bright that if it were placed at the center of our solar system, it would outshine the full moon by hundreds of thousands of times. Imagine a star whose light, if it were only a few hundred light-years away, would dominate the night sky, casting shadows even at midnight. And yet, because it is located in another galaxy altogether, its glow vanishes into the background, requiring some of the most advanced scientific instruments humanity has ever built to detect it. This is a humbling reminder of the sheer scale of the cosmos. Brilliance on a galactic level can be reduced to invisibility by nothing more than distance and dust. The invisibility of a 136A1 also underscores why astronomers rely so heavily on technology to explore the universe. Our eyes, marvelous as they are for survival on Earth, are woefully inadequate when it comes to the cosmos. We evolved to see sunlight reflected off the ground, not ultraviolet photons traveling across intergalactic space. That's why we build telescopes, to extend our senses, to reveal what our eyes cannot perceive, to lift the veil from stars like a 136A1. There's also a poetic element here. Humanity has always looked up at the stars and drawn inspiration from what we see: constellations, myths, navigation. But a 136A1 reminds us that the greatest wonders are not always visible to the naked eye. Sometimes the most extraordinary truths are hidden, waiting to be uncovered not by our direct senses but by our curiosity, ingenuity, and persistence. It's a star that teaches us humility. The universe doesn't bend itself to be visible to us. Instead, we must reach outward, with instruments and imagination, to glimpse its full grandeur. If a 136A1 were only 1,000 light-years away, it would blaze in our skies as a second sun, visible even during the day, outshining every star and planet at night. Entire human cultures would have been shaped around its presence, myths spun about its unending brilliance. But instead, it lies far away, quietly anonymous to anyone who doesn't know where to point a telescope. That contrast, the star's hidden brilliance, is what makes its invisibility almost poetic. It's the universe's way of reminding us that the most powerful forces often lie beyond what we can see with our own eyes. When astronomers classify stars, they aren't simply giving them labels for convenience. They're placing them into categories that reveal their life stories, their internal physics, and their ultimate destinies. For R136A1, the classification that best describes its current state is Wolf-Rayet star, a title reserved for some of the most extreme and short-lived stellar objects in the universe. Being a Wolf-Rayet star tells us that a 136A1 is not only massive and luminous, but also unstable, volatile, and shedding its mass at a breathtaking rate. In many ways, the Wolf-Rayet designation is less of a simple label and more of a warning. This is a star burning at the edge of survival, a cosmic giant tearing itself apart with its own ferocity. The Wolf-Rayet class was first identified in the 19th century by French astronomers Charles Wolf and Georges Rayet, who noticed peculiar emission lines in the spectra of certain stars. Unlike most stars, which show absorption lines from cooler gases in their atmospheres, these stars displayed bright emission lines that indicated powerful, high-velocity outflows of gas. In other words, their spectra revealed that material was not simply sitting still on the surface but was being hurled into space at thousands of kilometers per second. Today, we know these stars represent a late and unstable evolutionary phase of very massive stars, and a 136A1 fits perfectly into this category. So, what does it mean for our 136A1 to be a Wolf-Rayet star? At its core, it means the star has become so luminous, so hot, and so unstable that it can no longer hold on to its outer layers. The radiation pressure generated by its own light is literally blowing the star apart. Every second, powerful stellar winds are ripping material from its surface and flinging it into interstellar space. For a sense of scale, consider this: our Sun loses about 1 million tons of mass per second in the form of the solar wind. That may sound impressive until you compare it with a 136A1, which is losing billions of tons per second. Over the course of just a year, our 136A1 can shed as much mass as the Sun loses in thousands of years. These winds move at millions of kilometers per hour, carrying with them the raw material of the star's outer layers. As they crash into surrounding gas and dust, they produce shocks, sculpting the nebula and enriching it with heavier elements forged inside the star. In this way, Wolf-Rayet stars like a 136A1 are not just destructive, they're also creative, seeding their surroundings with the ingredients for future generations of stars and planets. Wolf-Rayet stars are further divided into subtypes, depending on the chemical fingerprints seen in their emission spectra. Some display strong lines of helium and nitrogen, classified as WN type, while others show carbon and oxygen, WC or WO types. These signatures tell astronomers what layers of the star are being exposed as the winds peel away its outer envelopes. Our 136A1, specifically, falls into the WN category, which means its surface is dominated by helium and nitrogen. This is significant because it suggests the star has already burned through much of its hydrogen in its core, fusing it into helium, and that nuclear ashes from deeper inside the star are being revealed at the surface. In other words, our 136A1 has evolved rapidly through its early life and is now exposing material that most stars keep hidden until much later stages. This classification also tells us something profound about the star's future. Wolf-Rayet stars are on borrowed time. Their extreme mass loss and unstable fusion processes guarantee that they won't last long on cosmic timescales. For our 136A1, this is especially true. By shedding so much mass, it is actively rewriting its own destiny. Each solar mass blown away by its winds changes the balance of gravity, pressure, and fuel in its core, steering it toward an inevitable catastrophic end, likely a supernova, hypernova, or direct collapse into a black hole. It's worth highlighting how unusual it is for a star to be a Wolf-Rayet at all. The vast majority of stars in the universe never reach this stage. Our Sun, for example, will die a quiet death as a white dwarf after swelling into a red giant. Stars of intermediate mass may explode as supernovae but rarely become Wolf-Rayets. Only the most massive, luminous, and short-lived stars, those born with tens or even hundreds of solar masses, go through this phase. They represent a fraction of the total stellar population, making them rare jewels of astrophysics. And a 136A1 is not just any Wolf-Rayet, it is perhaps the most extreme example of the class we have ever observed. Another feature of Wolf-Rayet stars is their spectacular stellar winds interacting with their environments. Many Wolf-Rayet stars are surrounded by glowing shells or bubbles of gas, created as their winds plow into surrounding material. While our 136A1 is embedded in the dense A136 cluster and the Tarantula Nebula, astronomers suspect that its winds are already shaping its surroundings in dramatic ways, carving cavities and enriching the interstellar medium with processed elements. The fingerprints of Wolf-Rayet activity can be seen in the turbulent gas structures of the Tarantula Nebula, which is glowing not only from a 136A1's radiation but also from the energetic impact of its outflows. There's also an important theoretical angle here. For decades, astronomers believed that stars above about 150 solar masses should not exist. The reasoning was simple. Beyond that limit, the radiation pressure from the star's own light would be so great that it would blow away any additional material trying to accrete onto the star during its formation. And yet, our 136A1 exists, weighing in at 200 to 250 solar masses, and classified as a Wolf-Rayet star. That means it is actively defying the models, forcing scientists to refine their theories about both star formation and stellar evolution. Wolf-Rayet stars like our 136A1 are laboratories for studying physics at the edge of possibility. And finally, there's the human element. The Wolf-Rayet classification gives a 136A1 a personality of sorts. It is not a quiet, stable star like our Sun, dutifully burning for billions of years. It is a tempestuous giant, living fast and burning out quickly, screaming its presence into the cosmos with winds, radiation, and fury. To call a 136A1 a Wolf-Rayet star is to acknowledge that it is in the middle of its death throes already, even while it shines with unrivaled brilliance. It is a star that embodies both power and fragility, magnificent in its output, yet doomed by the very processes that make it extraordinary. When we talk about the surface temperature of a 136A1, we are entering a realm so extreme that even our most familiar points of comparison, the sun, fire, molten lava, fall utterly short. Our 136A1's surface burns at around 50,000 Kelvin, which translates to nearly 50,000 degrees Celsius, or about 90,000 degrees Fahrenheit. That is almost 10 times hotter than the surface of our Sun, which has a relatively cool surface temperature of about 5,800 Kelvin. This difference is not a small step, it's a giant leap into a regime of physics few stars ever reach. The Sun's surface, or photosphere, emits the golden white light that sustains life on Earth. But our 136A1 surface, at 50,000 K, emits light heavily skewed toward the ultraviolet part of the spectrum. This means much of its output is invisible to the human eye. If you could look directly at a 136A1 from a safe distance, which, of course, is impossible, it would appear as a piercing bluish-white star, far brighter and harsher than any we see in our night sky. Its light would not feel warm, it would feel deadly, saturating everything in ultraviolet radiation powerful enough to ionize atoms and strip electrons from molecules across vast distances. To appreciate this, let's compare with other familiar heat sources. The hottest flames on Earth, such as those from oxyacetylene torches used to cut steel, reach around 3,500 Kelvin. Lava from a volcanic eruption tops out at around 1,500 to 2,000 Kelvin. Even the surface of Sirius, the brightest star visible from Earth, burns at about 10,000 Kelvin, which is still only a fraction of a 136A1's ferocity. In this context, our 136A1's surface temperature is not just hotter, it is qualitatively different. It moves the star into a category where normal matter behaves differently, where radiation dominates, and where atomic processes are stretched to their limits. At 50,000 Kelvin, hydrogen on the star's surface is not in the form we know. Instead of simple atoms with electrons neatly orbiting protons, the searing radiation keeps hydrogen largely ionized, stripped of its electrons entirely. Helium and heavier elements are also highly ionized, leaving the star's outer layers as a chaotic soup of nuclei and free electrons. This is part of why our 136A1 is classified as a Wolf-Rayet star. Its intense temperature and luminosity mean that its atmosphere is not calm or contained, but instead being blasted outward in violent stellar winds. The implications of such extreme heat ripple outward across the star's entire environment. That radiation ionizes the surrounding gas of the Tarantula Nebula, lighting it up like a cosmic lantern. The glowing tendrils we see in telescope images of the nebula are essentially fluorescent clouds, energized by ultraviolet photons pouring out of stars like a 136A1. Without stars this hot, the nebula would remain dark and invisible. In this sense, a 136A1 acts as both furnace and lighthouse, its heat and light shaping the very appearance of its galactic neighborhood. Temperature also plays a central role in stellar structure and stability. The Sun, for example, has a delicate balance between gravity pulling inward and thermal pressure pushing outward, maintained by its internal fusion processes. For our 136A1, the outward pressure from its 50,000 K surface and the radiation produced by it is so intense that it teeters on the edge of stability. The star is constantly fighting against its own light, which tries to blow it apart. The Eddington limit, a theoretical boundary where radiation pressure equals gravitational pull, is something a 136A1 dances dangerously close to. Its temperature and brightness are so extreme that it is only barely held together by its own gravity, which is enormous due to its massive bulk. Another striking point about the surface temperature is how it shapes the star's color and spectrum. Stars cooler than the Sun appear orange or red, while hotter stars shine white or blue. Our 136A1, with its blistering temperature, is firmly in the category of O-type stars, the hottest spectral class. Its spectrum is filled with broad emission lines, produced as high-energy radiation interacts with the ionized gases in its atmosphere. These spectral fingerprints allow astronomers to study its composition and confirm its Wolf-Rayet nature. Now let's imagine for a moment what such heat would mean if it were somehow transplanted closer to us. If a 136A1 replaced our Sun, the Earth would not simply be scorched, it would be stripped to its atomic skeleton. Ultraviolet radiation from a 50,000 K surface would obliterate the ozone layer instantly, sterilize the surface of the planet, and boil the oceans away in days. Even gas giants like Jupiter would not survive intact. Their atmospheres would be blasted into space by the torrent of radiation. At that distance, the concept of habitability would not exist. Life would not even have the chance to emerge, because the star's surface temperature would guarantee an environment hostile to all chemistry beyond plasma physics. It's also important to note that while the surface burns at 50,000 K, the core temperature of our 136A1 is even more mind-bending. At its heart, where fusion occurs, temperatures soar into the tens of millions of Kelvin, similar to or higher than the Sun's core, but under far greater pressure due to the star's immense mass. The 50,000 K surface we discuss is just the outer skin of this beast, radiating the unimaginable power generated deep within. This temperature also accelerates the star's evolution. In astronomy, hotter stars live faster and die younger. The Sun's modest temperature allows it to burn hydrogen slowly and steadily for 10 billion years. But a 136A1's blistering heat is the outward sign of its furious pace of fusion. It burns hydrogen at an extraordinary rate, consuming its fuel in just a few million years. The hotter the star, the shorter its life, and a 136A1 epitomizes this rule. Its surface temperature is both a badge of glory and a death sentence. Finally, there's a philosophical aspect. Humans experience heat as an immediate, tangible thing, the warmth of a fire, the burn of the sun on your skin. But when we speak of 50,000 K, we're describing a realm of heat that no human has ever felt and no earthly process can reproduce on a global scale. It's a temperature that exists only in the hearts of stars and in the brief flashes of nuclear detonations. To know that a single star can maintain such heat across a surface millions of kilometers wide for millions of years is to glimpse the sheer majesty of nature's power. In short, our 136A1's surface temperature of 50,000 K is not just a number. It's a window into the extremes of stellar physics. It tells us why the star shines so brightly, why it sheds mass so violently, why it destabilizes its surroundings, and why it cannot live long. It is the heat of creation and destruction combined, a blazing outer shell that both defines the star and seals its fate. Radiation is usually something we think of as invisible light, as the warmth we feel from the sun on our skin, or as a force that travels across space carrying information about distant galaxies. But in the case of our 136A1, radiation is not just a background presence, it is a force so powerful that it nearly tears the star apart from within. The concept we need to understand here is radiation pressure, the outward push created by light itself. In most stars, radiation is balanced by gravity, creating stability. In a 136A1, however, this balance teeters on the edge of collapse because the sheer intensity of its radiation is almost overwhelming. Every second, our 136A1 pours out energy at a level that boggles the imagination. Its luminosity is estimated to be several million times that of the Sun. That means every second, it emits more energy than the Sun produces in days, perhaps even weeks. This energy does not just stream outward harmlessly, it interacts with the very material of the star itself. Photons, those tiny packets of light, exert pressure when they strike particles. Normally, the effect is negligible. But in our 136A1, the flood of photons is so immense that it produces an outward force comparable to the inward pull of the star's gravity. This is the essence of radiation pressure. Now, think of the forces at work inside the star. Gravity is constantly pulling inward, trying to collapse the star under the weight of its own 200 to 250 solar masses. At the same time, fusion in the core generates an immense outpouring of light and energy, creating radiation pressure that pushes outward. For stars like the Sun, gravity comfortably outweighs radiation pressure, creating a long-lived, stable equilibrium. But in our 136A1, radiation pressure is so strong that it nearly equals gravity. This delicate balancing act places the star dangerously close to the Eddington limit, the theoretical maximum luminosity a star can sustain before its own light blows its outer layers into space. What this means in practice is that a 136A1 is in a constant battle with itself. Its inner regions desperately try to hold the star together, while its surface layers are being pushed outward by the relentless onslaught of photons. The result is violent. Mass loss. The star sheds material in powerful winds that carry billions of tons of gas into space every second. Unlike the Sun's gentle solar wind, these are hurricane-force gales of atomic matter, driven by radiation pressure so intense it reshapes the star's structure. To visualize this, imagine standing on the surface of our 136A1, if such a thing were possible. You would not feel a breeze of escaping gas. You would be vaporized instantly by ultraviolet radiation. But conceptually, you could picture the atmosphere boiling away, not because of heat alone, but because photons are literally hammering the star's outer layers outward. It's as though the star is shining so fiercely that it is unmaking itself with its own brilliance. The effects of this radiation power extend beyond the star. As those winds flow outward, they crash into the surrounding interstellar medium, compressing and heating nearby gas. In regions like the Tarantula Nebula, this process shapes towering pillars, filaments, and cavities, cosmic sculptures carved by radiation and wind. The nebula itself is a glowing testament to the raw energy radiating from stars like a 136A1. Without radiation pressure driving this chaos, the nebula would be dark, dormant gas. Instead, it glows like a galactic furnace, alive with turbulence and light. Astronomers are especially fascinated by the fact that radiation pressure makes stars like a 136A1 unstable. When a star approaches the Eddington limit, even small fluctuations in energy output can lead to dramatic changes in the star's behavior. For example, localized eruptions or outbursts can eject massive amounts of material into space, temporarily lowering the star's luminosity or altering its outer structure. In some cases, stars this luminous experience giant eruptions that mimic supernovae but leave the core intact, a phenomenon seen in luminous blue variables, which are closely related to Wolf-Rayet stars. Though our 136A1 has not yet been observed erupting in this way, its extreme radiation power makes such events plausible. From a theoretical perspective, radiation pressure also raises critical questions about star formation. If stars above ~150 solar masses were thought impossible because of radiation blowback, how did our 136A1 ever form at over 200 solar masses? Did it build up mass in a protected pocket of dense gas, shielded from its own light? Did it perhaps form through stellar mergers in the crowded A136 cluster, sidestepping the normal rules of star birth? Radiation pressure is the barrier, the roadblock, and a 136A1's existence tells us that somehow, in defiance of expectations, this roadblock was bypassed. Another dimension of radiation pressure is its role in determining the star's lifespan. Because so much energy is radiating outward, a 136A1 burns through its nuclear fuel at a furious pace. It is like a car engine revving at maximum throttle constantly, burning through fuel far faster than a gently idling motor. Radiation is both the expression of its immense power and the cause of its brief existence. The same photons that light up the nebula, that heat the gas, that shape the cluster, are also the ones driving a 136A1 toward an early demise. To really grasp the scale of its radiation, let's compare again with our Sun. The Sun emits about 3.8x 10 squared watts of energy. Our 136A1's output is estimated in the range of 10 cubed squared watts. That is 6 orders of magnitude greater. Imagine a star radiating so much power that if it were placed where the Sun is, Earth would be instantly obliterated, not by physical collision, but by sheer radiation pressure. The atmosphere would be stripped away, the oceans boiled into space, and the very rocks melted and vaporized. Our planet would be reduced to vapor in the glare of its photons. That is what radiation power on this scale means. And yet, in this destructive fury, there is also creation. Radiation pressure from massive stars drives chemical enrichment and star formation across galaxies. It pushes, stirs, and compresses clouds of gas, igniting new stars where once there was only stillness. Our 136A1, in fighting to hold itself together against its own radiation, also plays a role in the cycle of cosmic renewal. It is both destroyer and creator, its light simultaneously carving the nebula and sowing the seeds of future stars. In summary, the radiation power of our 136A1 is not just a characteristic, it is the defining struggle of the star's existence. Its brilliance is so extreme that it nearly rips the star apart, driving ferocious winds and testing the very limits of stellar stability. Radiation is the star's crowning achievement and its curse, the source of its beauty and the cause of its inevitable doom. At the heart of every star lies the process that defines it: nuclear fusion. For a 136A1, this process doesn't just happen. It rages at a pace so extreme that it makes our Sun look like a candle flickering beside a roaring furnace. To understand why our 136A1 shines with such intensity and why it lives such a short, turbulent life, we must look inside to its core, where hydrogen is being fused into helium at rates that defy ordinary comprehension. Fusion is, in essence, the act of turning mass into energy. In the Sun, hydrogen nuclei, protons, collide under immense heat and pressure, sticking together through the strong nuclear force to form helium. In the process, a tiny fraction of their mass is lost, converted into pure energy via Einstein's famous equation, E equals mc squared. This energy radiates outward as the light and heat we feel on Earth. The Sun does this steadily, producing enough energy to sustain itself for about 10 billion years. Now scale that up to our 136A1. With a mass roughly 200 to 250 times that of the Sun, the pressure and temperature in its core are on a completely different level. While the Sun's core reaches about 15 million Kelvin, our 136A1's core burns at tens of millions of Kelvin, possibly exceeding 50 million. At such temperatures, protons are moving so fast and colliding so violently that fusion occurs at rates thousands of times higher than in the Sun. The star is not just burning fuel, it is guzzling it, tearing through its hydrogen reserves with reckless speed. The specific fusion processes inside our 136A1 are also worth noting. In smaller stars like the Sun, the dominant mechanism is the proton-proton chain reaction, a relatively slow and steady process. But in massive stars like a 136A1, the primary engine is the CNO cycle, a catalytic chain of reactions involving carbon, nitrogen, and oxygen nuclei. In this cycle, hydrogen is fused into helium with the help of these heavier elements, which act as intermediaries. The CNO cycle is far more temperature sensitive than the proton-proton chain. As core temperatures rise, the reaction rate skyrockets. In a 136A1, where temperatures are so extreme, the CNO cycle runs at blistering speed, pumping out energy at levels unimaginable for ordinary stars. The result is the colossal luminosity we observe. Our 136A1 shines with millions of times the light of the Sun because its core is essentially a runaway nuclear furnace. Every second, it fuses a staggering quantity of hydrogen into helium, releasing torrents of photons that battle their way outward from the core, through the turbulent outer layers, and finally into space. These photons carry not only light but also the radiation pressure we've discussed, so much pressure that it nearly tears the star apart. But there's a catch. Burning fuel this quickly has consequences. If the Sun were like a slow, steady marathon runner, our 136A1 would be a sprinter at full speed, devouring its reserves in record time. While the Sun can pace itself for billions of years, our 136A1 will exhaust its hydrogen in just a few million years. This furious pace is written into its fate, a short, brilliant life followed by a spectacular death. Fusion is both the star's heartbeat and its ticking clock. Another fascinating aspect of fusion in such massive stars is how it alters their internal structure. In stars like a 136A1, the core doesn't sit neatly separated from the outer layers. Instead, the enormous energy flux drives convective mixing, a churning, boiling motion that stirs the star from within. This mixing dredges up elements from the core and circulates hydrogen fuel inward, effectively feeding the fusion process. It's like a pot of soup boiling so violently that the contents are constantly stirred, ensuring the hottest regions never run out of ingredients. This mixing allows a 136A1 to sustain its massive fusion output for as long as possible, though still on a tragically short timescale compared to stars like our Sun. As hydrogen fuses into helium, the star gradually accumulates heavier elements in its core. Eventually, helium itself will begin fusing into carbon and oxygen, though this stage happens later in the star's life. For now, the dominant story is hydrogen fusion at a pace unmatched by nearly any star we've ever observed. It's this process that powers the Tarantula Nebula, this process that fuels the violent stellar winds, this process that keeps a 136A1 teetering on the edge of stability. Fusion also explains why the star's surface temperature is so high. The energy radiating outward from the core must pass through the outer layers, heating them to 50,000 Kelvin. Without fusion driving this internal furnace, the star would collapse under its own weight. With fusion raging at these rates, it becomes one of the most luminous objects in the known universe. The sheer violence of this process makes a 136A1 an astrophysical laboratory. By studying it, astronomers can test theories of nuclear physics under conditions we could never replicate on Earth. No particle accelerator, no fusion reactor, no human-made experiment can match the pressures and temperatures in the core of our 136A1. It is nature's ultimate nuclear reactor, and it shows us what happens when physics is pushed to its absolute extremes. And let's not forget the poetic perspective. Inside this star, hydrogen, the most basic element in the universe, formed in the first minutes after the Big Bang, is being transformed into helium, the stuff of balloons and fireworks on Earth. But in this environment, that simple transformation becomes a spectacle of cosmic scale, releasing enough energy to light up a galaxy. Every second of our 136A1's life is a testament to the power hidden in the simplest building blocks of matter. Yet, this process carries within it the inevitability of change. As fusion races on, our 136A1 is already setting the stage for the next phases of its life: helium fusion, carbon fusion, oxygen fusion, and beyond. In a few million years, when the hydrogen runs out, the star's core will contract, temperatures will rise even higher, and fusion will proceed into heavier elements. Eventually, no amount of fusion will be able to hold off gravity, and our 136A1 will meet a cataclysmic end. In this sense, fusion is both the source of its brilliance and the architect of its demise. So, when we say our 136A1 is fusing hydrogen into helium at incredible rates, what we mean is this: it is a nuclear inferno, burning through its fuel with furious intensity, producing more energy in a second than our Sun can in days, living on the edge of stability, and racing headlong toward an inevitable and violent death. Fusion is the star's triumph, its burden, and its destiny, all at once. Instability is perhaps the single most defining trait of stars like our 136A1. To call it unstable is not to say it wobbles or flickers like a candle in the wind. Rather, it means the very forces that allow it to exist are so finely balanced, and so extreme, that the star cannot possibly maintain them for long. In the world of stellar physics, stability means harmony between gravity pulling inward and pressure pushing outward. But for our 136A1, that harmony is a fragile, temporary truce, constantly threatened by the star's own ferocity. At its core, the problem is this: our 136A1 is too massive for its own good. With a mass of 200 to 250 suns, its gravity is crushingly intense, pulling everything inward with unimaginable force. Ordinarily, this would lead to collapse, but the fusion reactions at its center generate equally colossal amounts of radiation and thermal pressure pushing outward. For most stars, this balance results in long-lived stability. But for R136a1, the balance teeters at the razor's edge, with radiation pressure coming dangerously close to overwhelming gravity. This is the precarious state we call radiative instability. Why is this instability so critical? Because it means a 136a1's life is measured not in billions of years, like our Sun, but in mere millions. Its furious rate of fusion, thousands of times faster than the Sun's, guarantees that its hydrogen fuel will be exhausted rapidly. And once the hydrogen is gone, the star must move to fusing helium, then heavier elements, in increasingly frantic attempts to stave off collapse. Each new stage burns hotter and faster, piling instability upon instability until gravity inevitably wins. This inherent instability also explains why our 136a1 is already shedding mass at such dramatic rates. The intense stellar winds driven by radiation pressure aren't just cosmetic features, they are the star's way of bleeding off excess energy in a desperate attempt to stay intact. But the winds don't solve the underlying problem. In fact, they create new instabilities. As the star loses mass, its internal structure shifts, altering the balance of pressure and gravity in unpredictable ways. These fluctuations can lead to violent eruptions, changes in brightness, or even partial collapses. Astronomers categorize some stars as luminous blue variables, LBVs, when they display these outbursts and instability-driven fluctuations. While our 136a1 is classified as a Wolf-Rayet star, it shares many characteristics with LBVs, especially the tendency toward erratic behavior caused by its immense luminosity. The sheer instability of its state means that it could, at any time, undergo a dramatic event, a sudden eruption of mass, a temporary dimming or brightening, or even a premature collapse. It's important to contrast this instability with the serenity of more familiar stars. Our Sun, with its modest mass and stable fusion, will enjoy billions of years of quiet life before it swells into a red giant and eventually becomes a white dwarf. Stars like our 136a1, by comparison, are doomed from the start. The very conditions that make them extraordinary, their mass, luminosity, and temperature, are the same conditions that seal their fate. Their brilliance is inseparable from their instability. The idea of instability also extends beyond the star itself to its influence on its environment. The violent winds and radiation that result from its unstable state inject chaos into the surrounding nebula. Gas clouds are compressed into new stars, while others are blasted apart. The region around a 136a1 is not calm or orderly. It is a stormy, turbulent cradle of creation and destruction, all driven by the star's instability. One particularly intriguing aspect of instability in stars like a 136a1 is that it challenges our theoretical models of stellar formation. According to many models, stars should not even be able to form with masses above about 150 suns, because radiation pressure would blow away incoming material before it could accumulate. And yet, a 136a1 exists, proof that either our models are incomplete or that unusual circumstances, like stellar mergers, created it. Its instability is not just a prediction of its future but a mystery of its past. How did a star this massive manage to come into being in the first place? And then there's the shortness of its life. Instability ensures that a 136a1 will not live to see the ages that stars like the Sun will. In just a few million years, a cosmic blink, it will consume its fuel, shed much of its mass, and collapse in one of the universe's most violent endings. For context, if Earth's entire 4.5 billion year history were compressed into a single calendar year, the Sun would last the full year and beyond. Our 136a1, by contrast, would flare briefly like a firework and then vanish within a few days of that cosmic year. This fleeting existence gives instability a poetic dimension. Our 136a1 is like a brilliant but short-lived flame, burning so brightly that it cannot endure. It is the embodiment of the phrase, "Live fast, die young." Its instability is not a weakness but the very essence of what makes it remarkable. It cannot survive long precisely because it is so extraordinary. Astronomers study instability in stars like a 136a1 not just to understand their fates but also to probe the physics of extreme environments. These stars serve as natural laboratories for testing theories of nuclear fusion, mass loss, radiation pressure, and stellar death. By watching how instability plays out in a 136a1, scientists refine our understanding of how stars influence their galaxies, how heavy elements are created, and how black holes are born. So when we say our 136A1 is unstable, we are saying it lives at the very edge of possibility. Its gravity and radiation are locked in a constant tug-of-war. Its winds scream outward at millions of kilometers per hour. Its brightness threatens to unmake it at any moment. And through it all, it shines with a brilliance unmatched in the known universe, even as instability ensures it will not shine for long. The story of our 136A1's lifespan is as dramatic as the star itself. If stars were people, our sun would be the wise elder, steady, patient, and content to live for billions of years. Our 136A1, by contrast, is the cosmic prodigy that burns too brightly, too quickly, destined to die young despite its brilliance. This is the paradox of the most massive stars. The more fuel they have, the faster they consume it, and the shorter their lives become. Let's set the numbers side by side. Our Sun, a modest G-type main sequence star with just one solar mass, will live for roughly 10 billion years. It's about halfway through its life now, at 4.6 billion years old. Its fuel consumption is measured, deliberate, and balanced. The Sun paces itself, fusing hydrogen into helium slowly enough that it will continue shining long after humanity has come and gone. Our 136A1, on the other hand, is born with 200 to 250 times more mass than the Sun. One might think that such a reservoir of fuel would mean an equally long, perhaps even eternal lifespan. But the opposite is true. Because of its immense mass, the pressures and temperatures inside its core are so high that fusion proceeds at a breakneck pace. Instead of sipping fuel like the Sun, our 136A1 guzzles it like a raging fire consuming dry timber. As a result, its entire main sequence lifetime is estimated to be only 2 to 3 million years. In cosmic terms, that is nothing, barely a blink in the universe's 13.8 billion year history. To put this into perspective, imagine Earth's 4.5 billion year history compressed into a single calendar year. In that analogy, the Sun would live and shine through the whole year, and then continue into the next. Our 136A1, by contrast, would flare into existence on January 1st and be gone before the end of the first day. That's how brief its lifespan is compared to the cosmic scale. This contrast highlights one of the most important truths in stellar physics. Massive stars live fast and die young. Their brilliance is inseparable from their brevity. The same forces that make them shine so brightly, their immense mass, high temperature, and furious rate of fusion, are the very forces that doom them to short lives. It is as though the universe allows them one moment of spectacular glory before snuffing them out. For astronomers, this fleeting lifespan makes a 136A1 and stars like it especially precious. They are rare not only because few stars are born with such enormous mass, but also because they don't survive long enough to be common. At any given time, only a handful of such giants exist in a galaxy. To study our 136A1 now is to catch it in its brief moment of brilliance, knowing that in only a few million years, it will be gone, exploded, collapsed, or transformed into a black hole. The Sun's long life, by contrast, has given Earth stability. For billions of years, the Sun's steady output of energy has created the conditions for life to emerge, evolve, and thrive. Planets around our 136A1, if any could exist, would not have that luxury. The star's life is too short and too violent for stable planetary systems, let alone life as we know it, to take hold. The Sun is like a calm, nurturing parent, while a 136A1 is a dazzling but destructive force, too intense, too short-lived, to allow for stability. Another way to think about this is through energy output. The Sun burns hydrogen slowly, conserving its reserves, like a lamp with a modest flame. Our 136A1, on the other hand, burns with the force of a raging bonfire, using up its fuel thousands of times faster. This is why the Sun can shine for billions of years, while a 136A1 can only manage a few million. Its extravagance is its downfall. And yet, there's a strange kind of poetry in this. The Sun's long life makes it reliable but ordinary. Our 136A1's short life makes it extraordinary but fleeting. It's a reminder that in the cosmos, brilliance and longevity rarely go hand in hand. The brightest stars are not the longest-lived, and the longest-lived stars are not the brightest. There's a cosmic trade-off between glory and endurance, and our 136A1 represents the extreme end of glory. From a scientific perspective, the short lifespan of stars like a 136A1 also has profound consequences for galaxy evolution. Because they die so quickly, they inject energy, heavy elements, and sometimes even black holes into their environments much sooner than smaller stars. In just a few million years, they can dramatically alter the structure of their host galaxy. In this sense, their short lives are not wasted. They leave behind legacies far larger than their brief existence might suggest. So, when we compare our 136A1's lifespan of a few million years with the Sun's 10 billion, we are not just contrasting numbers. We are contrasting two very different approaches to existence. The Sun's steady, enduring patience versus our 136A1's explosive, short-lived brilliance. One gives rise to stability and life. The other gives rise to cosmic upheaval and transformation. Both play essential roles in the universe's story, but in profoundly different ways. Mass loss is one of the defining features of a star like our 136A1. In fact, you could argue that its story is as much about what it loses as about what it has. When we picture a star, we usually think of it as a steady, stable ball of gas holding itself together for billions of years. But for our 136A1, the reality couldn't be more different. Its enormous mass, extreme temperature, and ferocious luminosity mean that it is constantly at war with itself, throwing off its own material in colossal stellar winds that strip it bare piece by piece. At the heart of this process lies radiation pressure. As we've discussed before, the light coming out of a 136A1 is unimaginably intense, millions of times brighter than the Sun. That light is not just illumination. It's energy, momentum, force. When photons stream outward from the star's core, they slam into the outer layers of gas. Normally, gravity holds those layers in place, but in a 136A1, the radiation pressure is so overwhelming that it literally blows the star's material away. This results in stellar winds so powerful they dwarf anything we see in our own solar system. For comparison, the Sun also has a stellar wind, a gentle outflow of charged particles drifting into the solar system. It carries away about 1 million tons of material every second. That might sound like a lot, but for the Sun, which weighs 2 times 10 cubed kilograms, it's practically nothing, like losing a grain of sand from a mountain each day. Our 136A1, however, operates on a completely different scale. Its winds are billions of times stronger than the Sun's, stripping away an estimated 10 solar masses per year. In simpler terms, this means that a 136A1 loses about the equivalent of the Sun's mass every few tens of thousands of years. For a single star, that's an astonishing hemorrhage of material. These winds are not quiet, invisible flows either. They are supersonic hurricanes of plasma blasting outward at speeds of thousands of kilometers per second. Imagine an Earth-sized planet caught in that storm. It would be stripped of its atmosphere instantly, its surface scorched beyond recognition. Nothing in the immediate vicinity of our 136A1 could ever hope to survive these conditions. Over time, this relentless shedding of mass transforms the star itself. In its youth, our 136A1 may have been even more massive, possibly starting life at 300 solar masses or more. But as the centuries tick by, it gradually slims down, losing much of its outer hydrogen envelope and exposing deeper layers of helium and heavier elements. This is why it is classified as a Wolf-Rayet star. These stars are defined by their strong stellar winds and their stripped-down, exposed cores. The very existence of Wolf-Rayet stars is proof of how devastating mass loss can be in the lives of massive stars. Mass loss also makes our 136A1's future unpredictable. The rate at which it sheds material will determine how it dies. If it loses enough mass before the end, it might collapse directly into a black hole without much of a show. If it retains more mass, it could explode as a spectacular supernova or even a hypernova, blasting its surroundings with unimaginable energy. In this way, mass loss is not just an incidental feature of a 136A1, it is one of the main factors shaping its destiny. There's also a ripple effect. The material that a 136A1 ejects does not vanish into nothingness. Instead, it enriches the surrounding nebula with heavy elements forged in the star's interior. Elements like carbon, nitrogen, and oxygen are carried into interstellar space by the winds, seeding the next generations of stars and planets. This is how massive stars pay it forward, recycling their substance into the cosmic ecosystem. Our own bodies, rich with carbon-based molecules, owe their existence in part to ancient stars that shed their mass billions of years ago. Our 136A1 is continuing this process on a grand scale, filling its region of the Large Magellanic Cloud with the ingredients for future creation. And yet, the violence of this mass loss cannot be overstated. To visualize it, imagine a star not as a calm beacon of light, but as a boiling cauldron, constantly spitting out its own essence into the cosmos. Each second, it is weaker than it was the second before. The process is both beautiful and tragic. The very thing that makes a 136A1 so magnificent, its radiation, is also the thing that is tearing it apart. What's fascinating is that mass loss doesn't just occur steadily. Astronomers suspect that in stars like a 136A1, the winds can vary in strength, sometimes flaring into enormous outbursts. These eruptions might hurl vast shells of material into space, leaving behind nebulae that glow with the light of the star. Other Wolf-Rayet stars in our galaxy are surrounded by such nebulae, shimmering reminders of their self-destructive power. Whether our 136A1 has already cast off such shells or will do so in the future is an open question, but its violent winds guarantee that its neighborhood will not remain untouched. Mass loss also deepens the star's instability. As it sheds its outer layers, the balance of pressure and gravity shifts. Each new loss alters the star's internal structure, sometimes making it flare brighter, sometimes dimmer, but always pushing it closer to its inevitable end. In this sense, a 136A1 is not simply burning through its life, it is literally tearing itself apart in the process. So when we look at our 136A1, we are not seeing a static object. We are seeing a star in flux, in motion, in decay. Its winds are stripping it constantly, reshaping it moment by moment. It is both creator and destroyer, both brilliant beacon and dying flame. Its mass loss is not just a detail, it is the central drama of its existence, the slow unraveling of the most massive star ever found. The ultimate fate of a 136A1 is one of the most fascinating and dramatic questions in modern astrophysics. For a star so massive and so energetic, the end is inevitable, but the exact manner of its demise is still a subject of active study and theoretical modeling. Unlike smaller stars that follow more predictable evolutionary paths, our 136A1's extreme mass, rapid fusion, and intense radiation pressure mean its death could take several extraordinary forms, each more spectacular than anything we experience in the solar system. The main contenders are supernova, hypernova, or direct collapse into a black hole, and each outcome is tied closely to the star's mass, composition, and the violent processes occurring in its core and outer layers. First, consider the classical supernova, the explosive death of a star that has exhausted its nuclear fuel. In a supernova, the core collapses under gravity, triggering a shockwave that blasts the outer layers into space. In a 136A1's case, a supernova would release an unimaginable amount of energy, briefly outshining an entire galaxy. Its stellar winds and mass loss leading up to this event would help determine whether the explosion is more or less symmetrical, affecting the distribution of heavy elements expelled into the surrounding nebula. A supernova from a star of this size would enrich the Large Magellanic Cloud with carbon, oxygen, and other elements critical for the formation of planets and life, a cosmic recycling process of extraordinary scale. However, our 136A1 may not follow the classical supernova path. Its mass is so extreme that some models predict a hypernova, a far more energetic version of a supernova. Hypernovae can release 10 times the energy of a typical supernova, producing incredibly powerful shockwaves and jets that penetrate deep into interstellar space. These events are rare and are thought to be responsible for some of the long-duration gamma-ray bursts, GRBs, we detect from distant galaxies. If a 136A1 were to end its life as a hypernova, it would become a cosmic beacon, its energy radiating across millions of light-years and potentially affecting neighboring star-forming regions. The intense energy release could also blow away nearby gas clouds, influencing the next generation of stars in the cluster. A third possible ending, and perhaps the most dramatic, is direct collapse into a black hole. In this scenario, our 136A1's core might become so dense that it overcomes all outward pressure without a visible explosion. The star's outer layers could either fall into the newly formed black hole or be partially ejected in violent bursts, but the event would be less luminous in visible light than a supernova or hypernova. Direct collapse is thought to be possible for stars exceeding roughly 150 to 200 solar masses, particularly if mass loss via stellar winds has reduced the star's outer envelope before collapse. The result is a black hole of extraordinary mass, potentially one of the largest stellar mass black holes ever formed. Such a black hole could later merge with others, contributing to gravitational wave signals detectable across the cosmos. Interestingly, the way our 136A1 dies is closely connected to its Wolf-Rayet phase and mass loss history. Its furious winds are stripping away its hydrogen envelope, exposing helium and heavier elements in the core. This gradual peeling may influence whether the star can undergo a classical supernova, a hypernova, or skip an explosive phase altogether and collapse directly into a black hole. In other words, the life it has lived, its extreme mass, rapid fusion, violent winds, and instability, determines how it dies. The star's death is not an isolated event but the culmination of everything that has happened to it over the past few million years. Some theoretical models even suggest the possibility of perinstability supernovae for stars as massive as a 136A1. In this scenario, extreme temperatures in the core produce electron-positron pairs, reducing the internal pressure that supports the star against gravity. This triggers a catastrophic contraction and then a thermonuclear explosion so powerful that it can completely unbind the star, leaving no remnant behind. No black hole, no neutron star, just a cloud of heavy elements scattered across space. While it's uncertain whether our 136A1 is massive enough and has the right composition to undergo a perinstability supernova, the mere possibility underscores the extremes involved. Another dimension to consider is the potential for gamma-ray bursts, GRBs. Some astronomers believe that the collapse of extremely massive, fast-spinning stars like a 136A1 could launch twin jets of energy at nearly the speed of light, producing GRBs visible across billions of light-years. These bursts are the most energetic events in the universe since the Big Bang and could briefly outshine entire galaxies. While a 136A1's rotation rate and exact mass loss history will determine whether it produces a GRB, the potential is there, making its eventual death not just a local event but a cosmic spectacle with far-reaching consequences. No matter which pathway our 136A1 ultimately takes, the consequences for its surroundings will be profound. Its death will inject massive amounts of heavy elements into the Tarantula Nebula and the broader Large Magellanic Cloud. These elements, carbon, oxygen, silicon, and iron, are essential building blocks for planets, complex chemistry, and eventually life. The shockwaves from its explosion will compress gas in neighboring regions, triggering new waves of star formation. In this way, our 136A1's death, while violent, becomes a catalyst for creation. A star that lives fast, dies young, and seeds the next generation of cosmic structures. It's also worth noting that the precise outcome remains one of the key mysteries of astrophysics. Observing stars this massive is rare, and no human has ever witnessed the death of a star quite like a 136A1. Scientists rely on computer simulations, theoretical models, and observations of similar massive stars elsewhere in the universe to make predictions. Each potential outcome, supernova, hypernova, direct collapse, or even perinstability supernova, carries slightly different consequences for the interstellar environment, the black hole population, and even the frequency of gamma-ray bursts detectable across the cosmos. In essence, the possible endings of a 136A1 encapsulate the ultimate drama of massive stellar evolution. Its entire life has been a battle of forces: gravity versus radiation, mass versus luminosity, stability versus chaos. Its death will be the final act, and whatever form it takes, it will illustrate on a grand scale the power, beauty, and fragility of stars at the extreme edge of physics. From this perspective, a 136A1 is not just a star. It is a cosmic experiment in the limits of nature, and its end will be the final and most spectacular proof of the laws governing the universe. The concept of gamma-ray bursts, GRBs, adds another layer of cosmic drama to the story of a 136A1. These events are among the most energetic and mysterious phenomena in the universe, capable of releasing in seconds as much energy as our Sun emits over its entire 10 billion-year lifespan. The potential for a star like a 136A1 to produce a GRB arises directly from its extreme mass, rapid rotation, and violent end-of-life scenarios. Understanding this possibility requires examining both the physical conditions within a 136A1 and the circumstances that produce these cosmic beacons. Gamma-ray bursts are not simple explosions. They are highly focused jets of electromagnetic energy, traveling at nearly the speed of light. For a GRB to occur, models suggest the progenitor star must be both massive and rapidly rotating. Our 136A1, with its 200 to 250 solar masses, intense luminosity, and Wolf-Rayet classification, fits many of the theoretical criteria. Its extreme mass ensures that when its core collapses, the gravitational energy released will be enormous. Its stripped-down, helium-rich outer layers, thanks to intense mass loss and stellar winds, allow jets of material to escape more easily than they would from a fully intact hydrogen envelope, which would otherwise absorb or deflect them. In particular, the collapsar model of GRBs is highly relevant for stars like our 136A1. According to this model, the core of a massive, rapidly rotating star collapses directly into a black hole. Surrounding material forms an accretion disk that funnels energy along the star's rotation axis, launching twin relativistic jets. These jets, composed of gamma-ray photons and highly energetic particles, pierce through the outer layers of the star and shoot out into space. If Earth happens to lie along the path of one of these jets, we detect the event as an incredibly bright, short-lived gamma-ray burst. The intensity of a potential GRB from our 136A1 would be staggering. Some models estimate that a single GRB could release 10 joules of energy in seconds, equivalent to the total energy output of the Sun over its entire lifetime. The sheer scale of such an event would not only affect the immediate stellar neighborhood but could be detectable across billions of light-years, illuminating distant galaxies and providing astronomers with clues about the early universe. It's important to note, however, that producing a GRB requires a precise combination of conditions. The star must retain enough angular momentum in its core to sustain a rotating accretion disk after collapse. Too much mass loss, and the core's rotation slows, reducing the likelihood of jet formation. Too little mass loss, and the outer hydrogen layers could choke the jets, preventing a GRB from escaping. A 136A1's current state, as a Wolf-Rayet star with substantial mass loss but a still massive core, positions it intriguingly close to the threshold where such a burst could occur. The potential for a GRB is also linked to a 136A1's metallicity, or the abundance of elements heavier than hydrogen and helium. Stars with lower metallicity lose less mass over their lifetimes, preserving more of their rotation and core mass, which increases GRB likelihood. The Large Magellanic Cloud, home to a 136A1, has slightly lower metallicity than the Milky Way, which may enhance the possibility that the star could produce a GRB rather than a more typical supernova or hypernova. While GRBs are extraordinarily powerful, they are also extremely directional. The jets are narrow, meaning that even if a 136A1 were to produce a GRB, it's almost certain that the Earth would not lie directly in the path of the beam. Nevertheless, the implications for the surrounding interstellar medium would be immense. A nearby GRB could compress or ionize gas clouds, trigger new waves of star formation, or even influence the evolution of other stars in the cluster. On cosmic scales, such bursts can drive chemical evolution and energy redistribution across galaxies. Observationally, studying the GRB potential of stars like our 136A1 is challenging. We have not yet witnessed a GRB from such a massive, nearby star, partly because the timing is unpredictable and the probability that the Earth lies in the line of sight is low. Instead, astronomers use indirect evidence from massive Wolf-Rayet stars, computational models, and distant GRB events in other galaxies to infer the likelihood and mechanisms of these bursts. Our 136A1 represents an ideal case study. Its extreme properties make it one of the most promising candidates for producing a GRB if it meets the precise rotational and structural conditions at death. There is also a broader significance to this. Gamma-ray bursts from stars like a 136A1 are thought to be responsible for some of the most energetic events in the early universe, potentially influencing galaxy formation and seeding interstellar space with heavy elements far earlier than ordinary supernovae could. They are markers of cosmic extremes, pushing the limits of how much energy a single star can release, and offering astronomers a rare window into the interplay between mass, rotation, and explosive death. In a poetic sense, the GRB potential adds another layer to a 136A1 story. It is not merely a massive, luminous star burning quickly. It is a ticking cosmic time bomb, holding within it the potential to unleash one of the most powerful phenomena known to science. Its brilliance, instability, and mass all combine to create a scenario where, If conditions align perfectly, it could briefly dominate the universe with a jet of light traveling at near-light speed, visible across billions of light-years. Even if a GRB never occurs, the theoretical potential underscores the extremity of our 136A1. It highlights how stars of such mass operate at the very boundaries of physics, challenging our understanding of stellar evolution, core collapse, and high-energy astrophysics. It is a reminder that the universe is capable of violence and spectacle far beyond ordinary human experience, and a 136A1 sits at the center of that dramatic frontier. The death of our 136A1 will not be a quiet event. It will be a transformative act for its entire cosmic neighborhood. One of the most important consequences of massive stars dying is the enrichment of space with heavy elements, the building blocks of planets, moons, and even life itself. To appreciate the scale of this impact, it helps to understand the process by which massive stars produce these elements and how they distribute them across the interstellar medium. Throughout its life, our 136A1 has been forging heavier elements in its core through nuclear fusion. Beginning with hydrogen fusion into helium, it progresses as its core contracts and heats up, eventually producing elements like carbon, oxygen, neon, magnesium, and silicon. In the final stages of its life, even heavier elements up to iron are formed in the innermost core. For smaller stars, much of this material remains locked away, and only a fraction is returned to space at the end of their lifetimes. For a star as massive as a 136A1, however, a substantial portion of these elements is destined to be ejected during its death, either through supernova or hypernova explosions or via its already powerful stellar winds during its Wolf-Rayet phase. When a 136A1 reaches the end of its life, the explosion will act as a cosmic dispersal mechanism. The shockwaves generated in the explosion will blast its enriched outer layers into the surrounding nebula, scattering heavy elements over vast distances. This is not a gentle sprinkle. It is an intense, violent redistribution of matter, capable of influencing hundreds of light-years around the star. The nearby Tarantula Nebula, already sculpted by the star's radiation and winds, will be further enriched, providing raw materials for the next generation of stars, planets, and potentially life-bearing systems. The significance of this enrichment cannot be overstated. In astrophysics, elements heavier than helium are collectively called metals, even if they include carbon, oxygen, and nitrogen. These metals are essential for the formation of rocky planets and complex chemistry. Without massive stars like a 136A1, galaxies would remain dominated by hydrogen and helium, with little chance of forming planets or the complex molecules required for life. In other words, a 136A1 is actively participating in a cosmic recycling program, transforming the simple elements created in the Big Bang into the materials needed to build worlds. Moreover, the elements ejected by our 136A1 will seed nearby molecular clouds, compressing gas and triggering new star formation. When the shockwave from a supernova passes through a dense gas cloud, it increases pressure in the cloud, causing regions to collapse under gravity. This is how massive stars indirectly catalyze the creation of future stars. In this sense, the death of our 136A1 is both an ending and a beginning. It clears space while simultaneously planting the seeds for new cosmic life cycles. The distribution of heavy elements also has galactic-scale consequences. Over time, repeated deaths of massive stars like a 136A1 gradually increase the metallicity of their host galaxies. Higher metallicity affects how stars form, how they evolve, and even how planets form around them. Galaxies without massive stars remain poor in metals and are less likely to host the diverse planetary systems we see in the Milky Way and the Large Magellanic Cloud. Our 136A1's contributions, therefore, are a critical part of the ongoing evolution of its galaxy. Another remarkable aspect is the speed and energy of dispersal. Because a 136A1 is so massive and its winds and potential explosions so powerful, the elements are not slowly diffusing. They are launched at thousands of kilometers per second, racing across space and interacting with other interstellar material. This high-speed dispersal increases the efficiency of chemical mixing, ensuring that heavy elements are widely available rather than confined to a small pocket of space. In a few million years, the material expelled from a 136A1 could enrich regions far beyond the R136 cluster itself, influencing star formation across a substantial portion of the Large Magellanic Cloud. We can also consider the long-term cosmic legacy. When the ejected material cools, it can coalesce into new stars, planets, and possibly life-bearing environments. Every carbon atom in our bodies, every oxygen atom we breathe, likely originated in massive stars like a 136A1 that lived and died long before the Sun existed. The death of our 136A1 will perpetuate this cosmic tradition, contributing directly to the material cycle that makes planets and life possible. In this sense, its death is not simply destructive. It is creative on a galactic scale, laying the foundation for new structures, systems, and complexity. Even the composition of future stars will be affected. Stars forming in regions enriched by our 136A1 will contain higher proportions of heavy elements, affecting their luminosity, lifespan, and evolution. These enriched stars will also host planetary systems more likely to contain rocky worlds rather than purely gaseous ones. In this way, the death of a single massive star like a 136A1 can have cascading consequences that resonate for billions of years, shaping the architecture of its galactic neighborhood. Finally, there is a poetic dimension to this process. The same star that has lived so briefly and so violently, that has radiated unimaginable energy and fought instability for millions of years, will leave behind a lasting imprint on the universe. Its ashes, carbon, oxygen, silicon, iron, will mingle with the gas of its galaxy, become part of new stars, form planets, and perhaps one day, life. In essence, a 136A1's death is a profound act of cosmic generosity, turning its own destruction into the raw material for future creation. A 136A1 is more than just the most massive star we've observed. It is a direct challenge to our understanding of how stars form, pushing the boundaries of astrophysical theory and forcing astronomers to rethink the limits of stellar mass. For decades, theoretical models suggested that stars could not exceed a certain mass, roughly 150 solar masses, because of the enormous pressure exerted by radiation during formation. Beyond this limit, the radiation would blow away infalling material before the star could grow any larger. Yet a 136A1 exists at 200 to 250 solar masses, defying what was long considered a hard ceiling in stellar physics. To understand why this is such a remarkable challenge, we need to explore the physics of star formation. Stars form in dense molecular clouds, where regions of gas collapse under gravity. As material falls inward, it heats up, and the core of the forming star begins nuclear fusion. In smaller stars, this process proceeds relatively smoothly. But in massive stars, radiation pressure from the growing core becomes a formidable obstacle. As hydrogen begins fusing into helium, photons generated in the core exert outward pressure on the surrounding gas. The more massive the forming star, the stronger this radiation becomes. At some point, it was thought, this pressure would halt further accretion, effectively setting an upper limit on stellar mass. Our 136A1, however, shows that reality is more complex. Its existence implies that nature has ways of circumventing the theoretical limit, at least under certain conditions. One possibility is that a 136A1 formed in an exceptionally dense region of the R136 cluster, where surrounding gas was so tightly packed that gravity could overcome radiation pressure, allowing the star to continue growing beyond the previously assumed maximum. Another possibility is that it formed through stellar mergers, collisions between smaller massive stars in the crowded environment of the cluster. In such a scenario, multiple stars could coalesce to create a single extremely massive object, bypassing the usual formation constraints. The fact that a 136A1 exists also forces astronomers to re-examine their models of stellar structure and evolution. Traditional simulations often assumed stars above 150 solar masses could not form, or if they did, they would immediately lose mass via catastrophic winds until they fell below the limit. But a 136A1 retains a mass far above this, meaning that either its mass loss rate is lower than expected during formation or that stars in extreme environments can grow faster than the winds can strip them. This has broad implications for our understanding of the initial mass function, IMF, the distribution of stellar masses at birth, which is foundational for models of galactic evolution. Another critical factor is metallicity, the abundance of elements heavier than hydrogen and helium. Our 136A1 resides in the Large Magellanic Cloud, which has slightly lower metallicity than the Milky Way. Lower metallicity reduces the opacity of the star's gas, meaning photons are less likely to interact with matter and thus exert less radiation pressure. This would allow a star like a 136A1 to accumulate more mass before radiation becomes a prohibitive barrier. In other words, Its environment may have been crucial in allowing it to surpass the previously assumed mass ceiling. The discovery of a 136A1 has also fueled debate over whether there is an absolute upper mass limit for stars, or whether such a limit is more of a statistical trend. While stars above 150 solar masses are exceedingly rare, a 136A1 proves that the universe can occasionally produce outliers. This has consequences for our understanding of stellar populations in starburst regions, where massive stars form in dense clusters, and for the early universe, where low metallicity environments may have produced stars far more massive than we see today. Some of these primordial stars, known as population 3 stars, might have exceeded several hundred solar masses, playing a key role in early chemical enrichment and black hole formation. Our 136A1 could be a modern analog, giving us a glimpse into processes that shaped the early cosmos. The star also tests our understanding of stellar stability and feedback mechanisms during formation. If radiation pressure is nearly sufficient to halt accretion, then stars like a 136A1 must form under finely tuned conditions, where gravity, turbulence, and accretion flows interact in extreme ways. It is a living laboratory for studying how massive stars maintain equilibrium even while forming at the edge of physical limits. Observing its mass, luminosity, and wind properties provides real-world data to refine theoretical models that previously relied largely on simulations. In short, our 136A1 is not just an observational curiosity, it is a critical stress test for astrophysics. Its existence challenges assumptions about the maximum mass a star can attain, about how stellar winds limit growth, and about the influence of environment and metallicity in star formation. It forces astronomers to ask new questions. How do such stars form without tearing themselves apart? How common are they in extreme clusters or in the early universe? And how do these cosmic behemoths shape the evolution of galaxies over time? Finally, there is a philosophical dimension to this challenge. Stars like a 136A1 show that the universe is more inventive, more extreme, and more varied than our theoretical models sometimes allow. They remind us that science is not just about confirming limits, it is about discovering the exceptions that expand our understanding. Our 136A1, by existing, stretches the boundaries of what we consider physically possible, a shining testament to the universe's capacity for extremes. When it comes to comparing a 136A1 to other well-known giants like UY Scuti and Betelgeuse, it becomes clear just how unusual this star truly is. While all three are considered extreme by the standards of ordinary stars, they represent different types of stellar extremes, different dimensions in which a star can be giant. Our 136A1 dominates in mass and luminosity, UY Scuti in sheer size, and Betelgeuse in its familiar prominence in our night sky as a massive red supergiant. By exploring these differences, we can appreciate the diversity of stellar extremes across the universe. Let's start with UY Scuti, currently considered one of the largest stars in terms of radius. Estimates place UY Scuti at roughly 1,700 times the radius of the Sun, or about 7.5 astronomical units, meaning it could engulf the orbit of Jupiter if placed in our solar system. In contrast, our 136A1 has a radius of only about 30 to 40 solar radii, small in comparison to UY Scuti, but this is where the distinction between size and mass becomes critical. Despite its relatively modest radius, our 136A1 is 200 to 250 times the mass of the Sun, compared to UY Scuti's estimated mass of only 30 solar masses. In other words, our 136A1 packs vastly more material into a much smaller volume, making it far denser and far more gravitationally extreme. This difference highlights a key point. Bigness can mean very different things in astrophysics. UY Scuti stretches across an enormous volume but is relatively diffuse, a bloated red supergiant whose density is a fraction of the Sun's. Our 136A1, by contrast, is a compact powerhouse, radiating millions of times more energy than the Sun despite being far smaller in radius. In terms of stellar power and energy output, our 136A1 dwarfs even the largest red supergiants, emphasizing that luminosity and mass are sometimes more critical than sheer size in defining a star's extremity. Next, consider Betelgeuse, the iconic red supergiant in Orion. Betelgeuse is closer to Earth, around 700 light-years away, which makes it a prominent feature of the night sky. Its radius is about 1,000 times that of the Sun, and its mass is estimated at around 20 solar masses. Like UY Scuti, Betelgeuse demonstrates the dramatic bloating of a star in its late evolutionary stages. But again, its mass and energy output are dwarfed by our 136A1. Betelgeuse shines at about 100,000 times the Sun's luminosity, which seems impressive, but it is millions of times fainter than a 136A1, which releases energy on a scale almost impossible to comprehend. Another critical distinction is stellar type and evolutionary stage. Both UY Scuti and Betelgeuse are red supergiants, cool, expanded stars nearing the end of their lifetimes. Their red color reflects a relatively cool surface temperature, about 3,500 to 4,000 Kelvin, compared to a 136A1's 50,000 Kelvin, nearly 10 times hotter. This difference in temperature underscores how a 136A1 is not just massive but also extraordinarily energetic. Its blue-white color signifies extreme fusion activity in its core, whereas UY Scuti and Betelgeuse have slowed their fusion, expanded, and cooled as part of their natural life cycle. We can also look at lifespan differences. Red supergiants like UY Scuti and Betelgeuse, while massive, live longer than stars as extreme as a 136A1. Betelgeuse, with roughly 20 solar masses, is expected to last several million years, whereas a 136A1, burning through fuel at breakneck speed, will exhaust its hydrogen and progress through later stages in only 2 to 3 million years. This contrast highlights how extreme mass correlates with short life, while extreme size does not necessarily imply the same rapid timeline. Even mass density tells a stark story. UY Scuti, with its vast radius and relatively modest mass, is a star that could be described as fluffy in astrophysical terms. The density of its material is incredibly low, almost comparable to air at sea level on Earth. Our 136A1, in contrast, is a tightly packed powerhouse, far denser and more extreme in terms of gravity, core pressure, and fusion rates. This makes a 136A1 an entirely different kind of cosmic giant, one of force, energy, and mass concentration, whereas UY Scuti is a giant in volume, and Betelgeuse is a giant in a combination of size and visibility to the naked eye. In terms of astronomical records, this comparison clarifies why a 136A1 is celebrated as the most massive star ever confirmed, even though it does not hold the title for the largest radius. UY Scuti grabs the crown for sheer size, Betelgeuse for familiarity and prominence in the night sky, and a 136A1 for raw mass, luminosity, and energy output. These distinctions illustrate that giant is not a single measure. Mass, radius, temperature, and luminosity all define different aspects of extremity in the stellar realm. Finally, the environments of these stars differ dramatically. Our 136A1 resides in the dense, younger 136 cluster within the Tarantula Nebula of the Large Magellanic Cloud, a region teeming with massive, young stars and intense radiation. This environment may have been essential for its formation, providing the gravitationally dense conditions needed to overcome radiation pressure and reach extreme mass. UY Scuti and Betelgeuse, by contrast, are isolated in the Milky Way, forming in more typical molecular clouds and evolving into their supergiant states over millions of years. The difference in environments highlights that cosmic context matters. Extreme stars like a 136A1 require not only extreme physics but also extreme neighborhoods. In summary, comparing our 136A1 to giants like UY Scuti and Betelgeuse emphasizes the diversity of cosmic extremes. Our 136A1 dominates in mass, energy output, temperature, and the physical challenges it presents to stellar physics. UY Scuti dominates in sheer radius, illustrating the bloated, diffuse side of stellar evolution. Betelgeuse dominates in fame and visibility, a massive, evolved star familiar from Earth's night sky. Together, they reveal the vast parameter space in which stars can be considered giant, and they underscore why a 136A1 is such a pivotal object for astrophysicists seeking to understand the limits of stellar physics. Our 136A1 holds a very special place in the astronomical record, but it is crucial to clarify what kind of record it holds. When we talk about biggest stars, people often imagine enormous, bloated red supergiants stretching across the orbits of planets. That mental image fits stars like UY Scuti or VY Canis Majoris, whose gargantuan radii make them the largest in volume. Our 136A1, however, is not among the largest in terms of sheer physical size. Its radius, around 30 to 40 times that of the Sun, is substantial but modest compared to red supergiants, which can exceed 1,500 solar radii. What makes a 136A1 extraordinary and deserving of its place in the record books is its mass, which is simply unprecedented. Mass is the ultimate measure of a star's potential energy, luminosity, and impact on its environment. Our 136A1's mass is estimated at 200 to 250 solar masses, making it the most massive star ever confirmed through direct observation and measurement. This is remarkable because it pushes theoretical boundaries. For decades, stellar models suggested that stars could not exceed about 150 solar masses, due to radiation pressure inhibiting further accretion of material during formation. Our 136A1 defies that limit, demonstrating that stars in certain extreme environments can grow far beyond what theory previously allowed. Its mass is the defining extreme, dwarfing any other stars in known clusters, including the largest red supergiants or well-known massive stars like Eta Carinii. The distinction between mass and size is key. While red supergiants are visually impressive due to their immense radii, much of their volume is tenuous outer layers with low density. Our 136A1, by contrast, concentrates a tremendous amount of matter in a relatively compact volume. This extreme density is part of what allows it to fuse elements at unprecedented rates, emit millions of times more energy than the Sun, and drive stellar winds powerful enough to reshape its surroundings. The mass, not the radius, is what defines its role as the universe's most extreme star. Our 136A1's astronomical record also includes its luminosity, which is intrinsically linked to its mass. A star's energy output scales steeply with mass. Doubling a star's mass increases its luminosity far more than proportionally. In our 136A1's case, its mass produces a luminosity estimated at 8.7 million times that of the Sun. This luminosity is part of why our 136A1 dominates its cluster and why it plays such a pivotal role in stellar physics studies. No other star comes close in this combination of mass and energy output, making it a natural benchmark for models of massive star evolution. Another aspect of its record is the rarity of such objects. Stars exceeding 100 solar masses are extremely uncommon. Stars like a 136A1, exceeding 200 solar masses, are rarer still, with only a handful known in the observable universe. This rarity adds to its significance. Every observation of a 136A1 provides astronomers with a rare opportunity to study the upper extremes of stellar physics, including core fusion rates, mass loss, stellar wind dynamics, and eventual end-of-life scenarios like hypernovae or direct black hole formation. It is not just the largest in mass, it is also a laboratory for understanding the universe's most extreme stars. It's also worth noting that a 136A1's record is carefully confirmed through observational techniques. Determining stellar mass at such distances, a 136A1 lies roughly 160,000 light-years away in the Large Magellanic Cloud, is incredibly challenging. Astronomers rely on a combination of spectroscopy, luminosity measurements, and cluster dynamics to estimate its mass. Its position in the dense R136 cluster complicates observations, because its light blends with neighboring massive stars. Despite these challenges, our 136A1's mass has been robustly estimated, giving it the distinction of being the most massive star directly confirmed by observation, rather than hypothetical or inferred from models alone. In essence, our 136A1's record is about extremes that matter most to physics: mass, energy output, fusion intensity, and influence on its surroundings. While other stars might appear larger visually or dominate our night sky due to proximity, none can match a 136A1 in raw physical power and mass concentration. Its place in the astronomical record is a testament not to superficial size but to the extraordinary physics that allow a star to exist at such extremes. In summary, our 136A1 demonstrates that the universe can create objects far more massive than once thought possible. Its radius may be modest compared to supergiants like UY Scuti, but its mass sets the standard for extreme stellar physics. It's a record holder not because it swells across vast distances, but because it concentrates unparalleled mass and energy into a single star, challenging our understanding of star formation, stellar evolution, and the limits of nature itself. Massive stars like a 136A1 are not just isolated cosmic curiosities, they are fundamental agents in the evolution of galaxies. While smaller stars quietly shine for billions of years, massive stars operate on a different scale entirely, influencing the structure, chemistry, and dynamics of entire galactic regions in ways that are both profound and long-lasting. Understanding this role requires examining the ways in which these stars interact with their environment throughout their life cycles, from intense radiation to violent stellar death. Even while still on the main sequence, our 136A1 exerts an extraordinary influence through its immense luminosity and radiation output. With a brightness millions of times that of the Sun, it floods its surrounding cluster with ultraviolet light and high-energy photons. This radiation ionizes the nearby gas, creating H2 regions, large clouds of ionized hydrogen that glow and expand outward. These ionized bubbles reshape the molecular clouds from which stars form, sometimes compressing regions to trigger new star formation, and other times dispersing gas and preventing star formation in certain areas. In essence, our 136A1 sculpts the landscape of its stellar nursery simply by shining. The star's stellar winds amplify this effect. As a 136A1 sheds material at incredible rates, equivalent to a sun's mass every tens of thousands of years, its fast-moving outflows collide with surrounding gas and dust. These collisions create shockwaves that can clear out cavities in the cluster, sweeping aside material and injecting kinetic energy into the interstellar medium. Over time, these winds contribute to galactic feedback, a process by which massive stars regulate star formation rates and influence the distribution of gas throughout their host galaxies. In dense clusters like a 136, where multiple massive stars coexist, these collective effects can dramatically shape the evolution of the region. The most dramatic influence, however, comes at the end of a star's life. The eventual supernova or hypernova of a star like a 136A1 releases incredible amounts of energy, far exceeding the combined luminosity of all stars in the Milky Way for a brief period. These explosions not only enrich the galaxy with heavy elements, as we discussed, but also drive shockwaves capable of compressing or dispersing entire molecular clouds. In some cases, supernova shockwaves can trigger bursts of star formation in nearby regions, while in others, they may inhibit star formation by blowing apart dense gas clouds. This dual role of both creation and destruction makes massive stars critical regulators of galactic evolution. Another aspect of their influence is the injection of momentum into the interstellar medium. The winds and explosions from massive stars stir the gas in their surroundings, creating turbulence on scales of tens to hundreds of light-years. This turbulence contributes to the mixing of chemical elements, the formation of filamentary structures in molecular clouds, and the redistribution of angular momentum within galactic disks. Without massive stars like a 136A1, galaxies would evolve in a far more static, chemically homogeneous manner, lacking the complex interplay of forces that gives rise to the diversity of stars, clusters, and nebulae we observe. Massive stars also have a profound effect on galactic chemical evolution. By synthesizing elements heavier than helium in their cores and releasing them through winds and explosions, they gradually increase the metallicity of their host galaxies. Higher metallicity changes how subsequent stars form, how they radiate energy, and how planetary systems emerge. Without stars like a 136A1 enriching the interstellar medium, later generations of stars and planets, including potentially habitable ones, would be fundamentally different. In a real sense, the evolution of galaxies is inseparable from the lives and deaths of their most massive stars. Additionally, our 136A1 exemplifies how extreme stars influence large-scale structures in starburst regions. The R136 cluster is one of the densest young star clusters known, and the energy output from stars like a 136A1 drives winds that escape the cluster entirely, affecting the surrounding Tarantula Nebula. These processes can regulate the growth of star clusters, shape the morphology of nebulae, and even contribute to galactic outflows that carry material into the intergalactic medium. The impact of a single massive star is amplified in such clusters, demonstrating how stars are not only local influencers but also agents of galactic scale change. Finally, the feedback from massive stars plays a role in the long-term evolution of galaxies by influencing star formation efficiency. Without massive stars, molecular clouds could collapse more freely, producing stars at higher rates. With them, energy input from radiation, winds, and explosions slows down or halts star formation in certain regions, preventing runaway collapse and helping galaxies maintain balance. In this way, our 136A1 and its peers act as regulators, controlling the pace and distribution of star formation, and ensuring that galaxies evolve in a dynamic, structured, and sustainable way. In summary, R136a1 demonstrates the multifaceted role massive stars play in galaxies. From intense radiation sculpting gas clouds, to stellar winds stirring the interstellar medium, to violent supernova explosions enriching and shaping their surroundings, massive stars are architects of galactic structure and evolution. Their influence extends far beyond their immediate vicinity, shaping star formation, chemical composition, and even the overall morphology of their host galaxies. Without stars like R136a1, galaxies would be dimmer, less chemically diverse, and less dynamic, showing that the most massive stars are not just extreme objects but essential drivers of cosmic evolution. R136a1 is not just a cosmic spectacle, it is also a revolutionary challenge to our understanding of stellar physics. Its extreme properties, unprecedented mass, luminosity, temperature, and mass loss rates, push the limits of traditional models of star formation and stellar evolution. Astronomers rely on observations of stars across the universe to build theoretical frameworks that explain how stars are born, live, and die. R136a1 doesn't merely test these frameworks, it forces them to be rewritten, refined, and reconsidered. One of the primary areas where R136a1 challenges astrophysics is in star formation theory. Traditional models predicted that radiation pressure from massive protostars should halt accretion once the star reached about 100 to 150 solar masses. Beyond this limit, the intense radiation emitted from the core would push away infalling gas, preventing further growth. Yet R136a1 exists at 200 to 250 solar masses, clearly showing that nature can bypass this limit. This discrepancy has prompted theorists to explore alternative formation mechanisms. Possibilities include accretion via dense, turbulent gas flows, where gravity overwhelms radiation pressure, and stellar mergers, where smaller stars collide in dense clusters to form a single supermassive object. Each of these scenarios has implications for understanding the upper end of the initial mass function, IMF, and the frequency of extremely massive stars in various environments. R136a1 also highlights the need for more sophisticated stellar evolution models. Its extreme mass leads to core conditions and fusion rates far beyond what is seen in ordinary massive stars. Hydrogen fusion occurs at a breakneck pace, and the star progresses through its life stages rapidly. Standard stellar models must be adjusted to account for these higher temperatures, stronger radiation pressure, and accelerated evolution. For instance, R136a1's core fusion may follow slightly different pathways due to the enormous pressures and temperatures, potentially producing heavier elements more efficiently or at different rates than predicted. Another challenge comes from mass loss and stellar winds. R136a1 sheds mass at rates previously thought impossible, on the order of 10 to 10 solar masses per year, with velocities reaching thousands of kilometers per second. Traditional models underestimated the impact of such intense winds on the star's evolution. They now have to include dynamic interactions between radiation pressure, wind acceleration, and the star's changing mass. The mass loss not only affects the star's lifespan but also its eventual fate, whether it explodes as a supernova, hypernova, or collapses directly into a black hole. R136a1 forces models to consider time-dependent, extreme mass loss scenarios rather than steady, low-rate approximations used for smaller stars. R136a1 also serves as a testbed for Wolf-Rayet physics. As a Wolf-Rayet star, it is in a phase where the hydrogen envelope has been stripped, exposing a helium-rich core. Observing R136a1 provides invaluable data about core composition, wind properties, and surface temperature, which refine our understanding of these rare, short-lived stages. For example, the star's extreme temperature of 50,000 Kelvin challenges models of radiative transfer and opacity in stellar atmospheres. Accurately modeling how energy flows through such a dense, luminous, and turbulent envelope is a cutting-edge problem in astrophysics, and R136a1 is one of the few real-world benchmarks available. Moreover, R136a1 informs theories about stellar instability and end-of-life predictions. Stars of this mass are inherently unstable due to the delicate balance between radiation pressure and gravity. Small perturbations can produce significant pulsations, eruptions, or changes in luminosity. Observing R136a1's behavior allows astronomers to test models of pulsational instabilities, mass ejection episodes, and pre-supernova dynamics, providing insight into the late evolutionary stages of the universe's most massive stars. The star also impacts high-energy astrophysics. Its extreme luminosity and mass loss rates generate intense stellar winds that produce shocks, X-ray emission, and ionization fronts in the surrounding medium. Understanding these processes helps refine models of stellar feedback, the mechanism by which massive stars regulate star formation and chemical enrichment in galaxies. Our 136A1 is an unparalleled laboratory for testing how energy and momentum are transferred from stars to their environments. Finally, our 136A1 influences cosmological models. Extremely massive stars like it may have been more common in the early universe, where low metallicity environments allowed stars to grow larger. Observing and modeling a 136A1 provides a local analog for population 3 stars, helping astronomers extrapolate the physics of the first stars, their impact on reionization, and their role in forming early black holes. Its properties help bridge the gap between modern observations and cosmological simulations, ensuring that theories of galaxy evolution and chemical enrichment are grounded in extreme but real examples. In short, our 136A1 forces astronomers to confront questions about the limits of physics under extreme conditions. Its existence challenges assumptions about mass limits, mass loss rates, fusion processes, stability, and environmental feedback. Each observation and measurement feeds directly into refining stellar models, improving our understanding of how the most massive stars are born, evolve, and die. Our 136A1 is more than a star. It is a natural laboratory at the extreme edge of stellar physics, reshaping our understanding of the universe and its most powerful objects. Humans have always been drawn to extremes, from the highest mountains to the deepest oceans, from the most intricate art to the most intricate equations of physics. In the cosmos, stars like a 136A1 represent the ultimate extremes, objects that exist at the limits of what nature allows. Studying such stars is more than a curiosity. It is a way to test the boundaries of physical laws, challenge our understanding of the universe, and confront questions about creation, destruction, and cosmic scale. Our 136A1, in particular, embodies extremes in mass, luminosity, temperature, and energy output, making it a perfect laboratory for pushing human knowledge to its limits. One fundamental reason we study our 136A1 is to understand the limits of star formation. Traditional astrophysical theories suggest that stars cannot form above about 150 solar masses, yet a 136A1 exceeds this, weighing in at 200 to 250 solar masses. This defiance of theory forces astronomers to explore how matter behaves under extreme gravity, pressure, and radiation. By observing a 136A1, scientists can refine models of accretion, radiation feedback, turbulence, and stellar mergers, all crucial processes in astrophysics. The star serves as a real-world counterexample to theoretical constraints, showing that nature sometimes outpaces our expectations. Another compelling reason is testing the laws of physics under extreme conditions. Our 136A1's core pressure, temperature, and fusion rates are far beyond anything achievable in human laboratories. Hydrogen fusion occurs at blistering speeds, surface temperatures reach 50,000 Kelvin, and radiation pressure pushes against the star's gravitational grip at phenomenal intensities. Observing and modeling these conditions allows astrophysicists to explore nuclear processes, energy transport, and stellar dynamics in regimes impossible to recreate on Earth. In essence, our 136A1 is a natural experiment on a cosmic scale, letting us see how matter behaves when pushed to extremes. We also study our 136A1 to gain insight into stellar evolution and end-of-life scenarios. Massive stars live fast and die young, and our 136A1 is a prime example. Its life will last only a few million years, culminating in either a supernova, hypernova, or direct collapse into a black hole. By studying the star now, scientists can make predictions about gamma-ray bursts, chemical enrichment, and black hole formation, helping us understand processes that affect entire galaxies. In doing so, our 136A1 becomes a bridge between the present and the future of its galactic environment. Studying our 136A1 also satisfies a deeper human drive, the quest for perspective. On Earth, we are accustomed to measuring objects by familiar scales, meters, kilometers, and masses within human experience. Our 136A1 exists on a scale that dwarfs our imagination. Its mass, luminosity, and energy output are almost incomprehensible. It emits in a single second more energy than our Sun will over its entire 10 billion year lifetime. Contemplating a 136A1 challenges our perception of scale, forcing us to appreciate the vastness and power of the universe while simultaneously realizing the fragility of our tiny blue planet. Another reason is the cosmic storytelling it enables. Stars like our 136A1 are storytellers of creation, evolution, and destruction. Its formation likely involved dense cluster dynamics, perhaps even stellar mergers, while its death will scatter heavy elements into the galaxy, contributing to the next generation of stars and planets. By studying it, we connect with the cycles of matter and energy that shape galaxies, essentially witnessing a narrative that has been unfolding for millions of years. Observing these extreme events allows humans to participate in a cosmic story far beyond our lifetimes, offering insight into the interconnectedness of matter, energy, and life in the universe. Our 136A1 also pushes technological boundaries. Its study has required high-resolution telescopes like Hubble, advanced spectroscopy, and now next-generation instruments like the James Webb Space Telescope. Observing this star challenges astronomers to refine observational techniques, improve instrumentation, and develop computational models capable of handling extreme data. In this sense, the star drives progress in science and technology, forcing us to innovate in order to probe nature at its limits. Finally, studying our 136A1 satisfies a fundamental philosophical and existential curiosity. Humanity has always asked, how far does the universe stretch? How powerful can a single object become? What are the ultimate limits of nature? Stars like our 136A1 provide concrete answers. They are living laboratories at the extremes of physics, showing us that the universe is capable of producing phenomena vastly beyond everyday experience. Observing and understanding them is a way for humans to grapple with questions of scale, power, and the boundaries of possibility. In essence, humans study our 136A1 because it is both a test of the laws of physics and a source of cosmic awe. It exemplifies the extremes of mass, energy, and temperature, forcing us to rethink star formation, evolution, and galactic dynamics. It challenges our models, stretches our imagination, and gives us perspective on the relative smallness of our world. Through our 136A1, we explore the limits of nature, confront the extraordinary, and deepen our understanding of the universe we inhabit. Studying our 136A1 is far from straightforward. Its extraordinary properties might seem obvious on paper: extreme mass, brightness, and temperature, but actually observing and measuring these properties presents a series of significant challenges. These challenges arise primarily from its enormous distance, the crowded environment of its host cluster, and the inherent limitations of even the most advanced astronomical instruments. Understanding these difficulties illuminates both the ingenuity required in modern astronomy and the perseverance behind each discovery about this cosmic giant. One of the most immediate challenges is distance. Our 136A1 is located in the Large Magellanic Cloud, LMC, roughly 160,000 light-years away from Earth. This immense separation means that even though the star emits millions of times the energy of the Sun, it appears as only a faint point of light from our perspective. Unlike nearby stars such as Betelgeuse, which can be resolved with modest telescopes, our 136A1 is effectively embedded in a sea of other stars within its cluster. Observing it requires high-resolution imaging capable of distinguishing the light of a 136A1 from surrounding sources, a task complicated by the limitations of diffraction and atmospheric distortion for ground-based telescopes. Compounding the distance issue is the crowded nature of its host, the R136 cluster. Our 136A1 does not exist in isolation. It is surrounded by dozens of other massive, luminous stars within a region only a few light-years across. From our vantage point, these stars are almost indistinguishable from one another without the aid of sophisticated techniques. Early observations from the 1980s, even with Hubble, initially could not separate a 136A1 from its close neighbors. The cluster is so dense that stellar light blends together, requiring astronomers to use deconvolution algorithms, adaptive optics, and precise photometric techniques to isolate a 136A1's properties. These methods allow researchers to extract its luminosity, temperature, and spectral characteristics with sufficient accuracy despite the crowding. Another difficulty arises from interstellar dust and gas. The Tarantula Nebula, where the R136 cluster resides, is filled with dust and ionized gas that absorb and scatter visible light. This means that much of the star's emitted energy is partially obscured or shifted to different wavelengths. To compensate, astronomers must rely on multi-wavelength observations, from ultraviolet to infrared, to capture the full picture. Infrared observations are particularly valuable because longer wavelengths can penetrate the dust, allowing astronomers to study the star's properties more accurately. Even with these tools, correcting for dust extinction requires careful modeling, as slight errors can lead to significant uncertainties in estimates of luminosity and mass. Spectroscopy, a primary method for determining a star's temperature, composition, and velocity, presents additional challenges. Because a 136A1's light is mingled with that of other nearby massive stars, its spectral lines can overlap or be contaminated, making it difficult to disentangle the features unique to this star. Furthermore, its intense stellar winds broaden spectral lines, further complicating precise measurements. Astronomers must employ advanced modeling to account for Doppler broadening, line blending, and wind-driven emission, carefully reconstructing the star's true spectrum from the complex data. Distance also complicates mass determination. Unlike stars in binary systems, where orbital dynamics provide a direct measure of mass, R136A1 is effectively a single star in a distant cluster, making direct mass measurements impossible. Astronomers instead rely on indirect methods, such as modeling its luminosity, temperature, and evolutionary state, in combination with stellar evolution models. Each of these steps introduces potential uncertainties, which is why the estimated mass range of 200 to 250 solar masses carries some error bars. Yet, even with these challenges, repeated observations and cross-verification using different techniques have confirmed a 136A1 as the most massive star known. Another layer of complexity comes from temporal variability. Massive stars like a 136A1 often exhibit fluctuations in brightness due to pulsations, eruptions, or changes in stellar wind density. Observations must therefore account for time-dependent variations, requiring multiple measurements over extended periods to obtain reliable averages. Single snapshots may misrepresent the star's true properties, leading to either overestimation or underestimation of luminosity and other critical parameters. Finally, studying our 136A1 demands the integration of data from multiple observatories and instruments. Ground-based telescopes, space telescopes like Hubble, and now instruments such as the James Webb Space Telescope, JWST, all contribute pieces of the puzzle. Each platform has its strengths and limitations. Hubble provides ultraviolet and optical resolution, JWST extends observations into the infrared, and ground-based observatories offer adaptive optics for high-resolution imaging. Coordinating these observations, calibrating data across different instruments, and reconciling measurements requires meticulous work and careful statistical analysis. In essence, observing a 136A1 is a triumph of modern astrophysics, requiring innovative technology, careful modeling, and repeated verification. Its distance, the crowded cluster environment, interstellar dust, spectral complexity, and intrinsic variability all pose significant challenges. Yet overcoming these difficulties has allowed astronomers to extract unprecedented insights about the most massive stars, from their mass and luminosity to their surface temperature and stellar winds. The effort highlights both the limitations of human observation and the ingenuity we apply to push beyond them, revealing a 136A1 as a shining example of how extreme objects can be studied even across unimaginable distances. The advent of next-generation telescopes marks a transformative era in the study of extreme stars like a 136A1, and among these, the James Webb Space Telescope, JWST, plays a particularly critical role. While earlier instruments such as the Hubble Space Telescope and ground-based observatories enabled the discovery and initial characterization of a 136A1, the limits of their sensitivity, resolution, and wavelength coverage left many details obscured. JWST, with its unprecedented infrared capabilities, high spatial resolution, and advanced spectroscopic instruments, is set to dramatically sharpen our understanding of this cosmic giant. One of the primary advantages of JWST is its ability to observe in the infrared spectrum, which allows it to penetrate the dense dust clouds of the Tarantula Nebula surrounding the R136 cluster. Dust absorbs and scatters visible light, creating uncertainties in measurements of luminosity, temperature, and mass. Infrared observations, however, bypass much of this obscuration, providing a clearer, more complete picture of the star's true brightness and surface characteristics. This is critical for our 136A1 because even minor errors in luminosity estimates translate into significant uncertainties in calculated mass, energy output, and evolutionary stage. By using JWST, astronomers can obtain more accurate photometry, essential for refining models of its structure and life cycle. JWST also offers higher spatial resolution than previous infrared instruments, allowing scientists to more effectively resolve our 136A1 from neighboring stars in its dense cluster. In crowded regions like the core of our 136, where multiple massive stars lie within a few light-years of each other, light blending has historically hindered precise measurements. JWST's sharp imaging and advanced adaptive optic systems will enable astronomers to isolate a 136A1's light, improving the accuracy of spectroscopic analysis. This clarity will help refine estimates of surface temperature, radius, and chemical composition, providing insights into the processes driving its extreme mass loss and energy output. Spectroscopy is another area where JWST will revolutionize our understanding. Its near-infrared spectrographs can detect subtle features in the star's spectrum, revealing details about stellar winds, surface abundances, and ionotation states that were previously inaccessible. For example, our 136A1's intense Wolf-Rayet stellar winds broaden spectral lines, making it difficult to determine composition and mass loss rates. JWST's high-resolution spectra will allow astronomers to model these winds more precisely, giving a clearer picture of how a 136A1 sheds material and evolves over time. This has implications not only for understanding this star but also for improving models of massive star evolution in general, particularly at the upper mass limit. Another crucial capability of JWST is its ability to monitor variability over time. Massive stars like a 136A1 often experience fluctuations in luminosity, eruptions, and changes in wind structure. By providing repeated, high-fidelity observations over months or years, JWST can track these variations, giving astronomers insight into instabilities in the star's outer layers and pulsational behavior. This time domain data is essential for understanding the pre-supernova evolution of massive stars and predicting potential outcomes, including supernova or gamma-ray burst scenarios. JWST also allows astronomers to probe the surrounding environment of a 136A1 in unprecedented detail. By examining the interactions between its stellar winds and the dense gas in the Tarantula Nebula, scientists can better understand how massive stars shape their natal clusters and trigger or inhibit subsequent star formation. Mapping these feedback processes in infrared light provides a more complete picture of how a 136A1's energy output regulates the evolution of the surrounding nebula. These studies are crucial for understanding galaxy evolution, as massive stars like a 136A1 play a disproportionately large role in shaping the dynamics and chemistry of their host galaxies. The ability to combine high-resolution imaging, precise photometry, and spectroscopy across multiple infrared bands makes JWST a transformative tool for a 136A1 research. Previous estimates of its mass, luminosity, and evolutionary state relied on indirect methods and modeling assumptions due to observational limitations. With JWST, astronomers can test these models against far more precise empirical data, reducing uncertainties and refining our understanding of extreme stellar physics. For example, mass loss rates, surface composition, wind velocity, and the structure of the star's outer layers can now be measured with unprecedented accuracy, providing direct inputs to stellar evolution simulations. Moreover, JWST's capabilities extend to detecting fainter companions or unresolved stars within the R136 cluster. This is important because interactions or past mergers with other massive stars may have contributed to a 136A1's extraordinary mass. By resolving nearby stars and potential binary components, JWST can help reconstruct the star's formation history, shedding light on whether it grew through accretion, mergers, or a combination of processes. This is a critical piece of the puzzle for understanding how nature can produce stars beyond the previously theorized 150 solar mass limit. In addition, JWST opens the door for studying early chemical enrichment and extreme feedback in ways impossible before. By measuring emission lines from ionized gas, astronomers can quantify how a 136A1's radiation and winds impact its cluster and the broader nebula, providing empirical evidence of the feedback mechanisms that shape starburst regions. This information is essential for linking stellar physics to galaxy-scale evolution, helping us understand not only the fate of our 136A1 but also its broader cosmic influence. Finally, JWST represents a bridge between observational astronomy and theoretical modeling. Observations of our 136A1 with this instrument will feed directly into simulations of supermassive star evolution, Wolf-Rayet winds, supernova precursors, and gamma-ray burst progenitors. Every new data point allows theorists to calibrate their models against an extreme but real example, refining predictions about how massive stars behave and die. In doing so, JWST doesn't just observe a 136A1, it transforms the star into a benchmark for the physics of the most extreme stars in the universe. In summary, JWST will redefine our understanding of a 136A1 by offering unparalleled infrared imaging, high-resolution spectroscopy, time-domain monitoring, and detailed mapping of its environment. It addresses challenges posed by distance, dust, crowding, and variability, enabling astronomers to study the star's mass, luminosity, winds, and chemical composition with unprecedented precision. By doing so, JWST allows humanity to probe one of the universe's most extreme objects in extraordinary detail, transforming a 136A1 from a distant point of light into a fully characterized laboratory for extreme astrophysics. Our 136A1, in all its staggering magnitude, offers not only a scientific spectacle but also a profoundly humbling perspective on our place in the universe. While astronomers focus on its mass, luminosity, and extreme fusion processes, there is a poetic dimension to contemplating such stars. They make the Earth, and even the Sun, seem vanishingly small by comparison. Standing metaphorically in the shadow of a 136A1, the scale of our daily concerns shrinks against the backdrop of cosmic enormity. To grasp this, consider that a 136A1's mass is 200 to 250 times that of our Sun. Our Sun, massive by human standards, accounts for over 99% of the solar system's total mass, yet a 136A1 dwarfs it entirely. If we imagine scaling down the Sun to the size of a basketball, a 136A1 would be roughly the size of a medium-sized beach ball in mass equivalence. But this analogy only touches the surface, because the energy output, temperature, and influence of the star extend far beyond simple size comparisons. In terms of luminosity, our 136A1 emits millions of times more energy than the Sun, enough in a single second to outshine the combined output of hundreds of thousands of suns if concentrated in a similar volume. Against this, Earth, our home, vibrant with life, is a tiny, fragile speck of rock, orbiting a star of comparatively modest scale in a quiet corner of the cosmos. Even radius, which for our 136A1 is around 30 to 40 times that of the Sun, emphasizes this perspective. If the Sun was scaled to the size of a typical front door, our 136A1 would be comparable to a modest room. But that room contains a concentration of energy, mass, and radiation that no earthly environment could endure. Standing metaphorically near such a star in imagination is an exercise in humility. The Earth would be a grain of sand, its oceans, atmosphere, and biosphere utterly negligible compared to the physical and energetic power of the star. The poetic dimension is further emphasized when we reflect on the star's life cycle and ultimate fate. In only a few million years, a mere blink on cosmic timescales, a 136A1 will either explode as a supernova or collapse into a black hole. This short life is a reminder that even the universe's mightiest forces are ephemeral, subject to the inexorable passage of time. Meanwhile, Earth spins in its orbit, experiencing eons in relative stability, yet still dwarfed in scale and energy by a star it could never hope to rival. This contrast, between the planet's delicate persistence and the star's explosive power, offers a meditation on human fragility, cosmic transience, and the grandeur of nature. Our 136A1 also invites reflection on perspective and awe. From our vantage point on Earth, it is invisible to the naked eye. Its brilliance is obscured by distance and interstellar dust. Yet it continues to burn with unimaginable power, shaping its surroundings, seeding future generations of stars, and embodying the extremes of physics. That such a colossal entity exists in a relatively nearby galaxy, yet remains imperceptible without sophisticated instruments, underscores the vastness of the universe and the tiny niche we occupy within it. In contemplating a 136A1, we are reminded that our sensory limitations hide much of reality from us, and that science is a tool to expand our perception, bridging the gulf between human scale and cosmic scale. There is also a poetic symmetry in the idea that elements forged in massive stars eventually make their way into planets like Earth. Carbon, oxygen, iron, essential for life, were created in the cores of stars that lived and died long before the solar system formed. In a way, stars like a 136A1 are ancestral architects of our very existence, a reminder that the tiniest forms of life on Earth are intricately connected to processes occurring in the hearts of cosmic giants. The poetic resonance is striking. The star's sheer mass and energy dwarf us physically, yet its internal processes are directly linked to the chemistry that sustains us. Moreover, our 136A1 forces contemplation of time and scale. Its life of a few million years is brief in stellar terms, yet vastly exceeds the timescales of human existence. Its energy output is unimaginable, yet all of it originates from nuclear reactions that obey the same physical laws familiar on Earth, from atomic fusion to radiation transfer. In this sense, the star is both alien and intimately connected, extreme, incomprehensible, and yet governed by the same universe that cradles our tiny planet. Finally, the poetic angle lies in the contrast between power and fragility. Our 136A1 represents extremes of mass, energy, and temperature, capable of reshaping its entire cluster. Yet even this mighty star is temporary. It exists in a fragile equilibrium, constantly shedding mass, facing instabilities, and ultimately destined for violent death. The Earth, conversely, appears small and vulnerable, but it endures, orbiting a comparatively modest star with stability sufficient for life to flourish. In contemplating both, we experience a humbling perspective on the fragility of existence and the grandeur of the cosmos. In essence, the poetic dimension of a 136A1 is its ability to expand human perspective. It dwarfs our world in size, mass, and energy, yet its processes are intimately tied to the chemistry and evolution that allow planets like Earth, and life itself, to exist. It reminds us of our fragility, our ingenuity in observing the unseen, and at the extraordinary extremes that nature can produce. Reflecting on a 136A1 encourages a dual sense of humility and wonder, connecting scientific knowledge with a profound emotional and philosophical appreciation of the universe. As we draw the journey of a 136A1 to a close, it becomes clear that this star embodies the paradoxical nature of cosmic extremes, immense power coexisting with profound fragility. Our 136A1 is the universe's heavyweight champion in mass and energy output, yet despite its seemingly invincible stature, it exists in a delicate balance, teetering on the edge of stability. Its very survival is fleeting on cosmic timescales, reminding us that even the most extraordinary stars are temporary actors on the stage of the universe. Our 136A1 demonstrates sheer power in every measurable aspect. Its mass, 200 to 250 times that of our Sun, creates gravitational forces capable of containing unimaginably energetic nuclear reactions at its core. Its luminosity, millions of times that of the Sun, floods its surroundings with intense radiation, reshaping the nebula in which it resides and influencing the formation of other stars. Its surface temperature, around 50,000 Kelvin, produces a blistering heat that would incinerate anything nearby, and its stellar winds carry away mass at phenomenal rates, injecting momentum and heavy elements into the surrounding cluster. Every aspect of our 136A1, from core to corona, is an exercise in extremity, a physical manifestation of nature pushing the limits of what a star can endure. Yet this power is counterbalanced by fragility and impermanence. Stars of this magnitude are inherently unstable, their lives brief and turbulent. Radiation pressure constantly fights against gravity, threatening to blow the star apart. Instabilities in the outer layers and the immense mass loss it experiences through stellar winds make a 136A1 a cosmic balancing act, surviving only because the forces within it remain in delicate equilibrium. Even a star capable of creating elements essential for life and reshaping its entire cluster is vulnerable to the very physics that enable its power. Its death, whether as a hypernova, supernova, or direct collapse into a black hole, will be as dramatic as its life, yet it is inevitable, a reminder that in the universe, nothing is permanent, and even the mightiest phenomena are subject to change. Our 136A1 also highlights the scale and scope of the cosmos in ways that humble human perspective. From Earth, it is invisible to the naked eye, distant by 160,000 light-years, yet its effects are immense in its local environment. Its presence reminds us of the extraordinary range of scales and energies in the universe, that a star can be simultaneously unobservable to us yet utterly transformative to its surroundings. Contemplating a 136A1 invites awe, not just at its power, but at the vast, intricate, and interconnected systems of which it is a part, from the dense 136 cluster to the Tarantula Nebula, and ultimately to galactic evolution itself. Moreover, our 136A1 embodies the limits of human knowledge and the triumph of human curiosity. It challenged theoretical models of stellar mass, pushed observational technology to its limits, and inspired new generations of astrophysical research. Observing and understanding it requires space telescopes, adaptive optics, and advanced spectroscopy, tools that stretch human ingenuity across the gulf of space and time. Our 136A1, in this sense, is both a cosmic teacher and a humbling reminder of the complexity of the universe. A star that exists at the threshold of what physics allows, and one that we can study only because of our persistent drive to explore. In reflecting on a 136A1, we are reminded that the universe is a place of contrasts: power and fragility, creation and destruction, permanence and ephemerality. This star channels the most extreme forces known in the cosmos, yet its life will end in cataclysm, feeding the next generation of stars and planetary systems. Its existence demonstrates the extraordinary processes that govern the universe and underscores the ephemeral nature of even the most formidable cosmic giants. The brilliance of a 136A1 illuminates not only the nebula in which it resides, but also the path of scientific inquiry and human understanding, pushing us to confront scales, energies, and durations far beyond ordinary experience. Ultimately, our 136A1 is a testament to the extremes of nature, a cosmic marvel that reveals the boundaries of what is possible in stellar physics. Its power reshapes clusters, seeds galaxies with heavy elements, and challenges our theoretical frameworks. Its fragility ensures that these feats are fleeting, emphasizing the transient, dynamic, and awe-inspiring nature of the universe. In contemplating a 136A1, we witness a cosmic drama of unmatched scale, one that reminds us that even in the immensity of space, life, matter, and energy are bound by forces that are both majestic and mercurial. For anyone looking up at the night sky and considering the vastness of the cosmos, our 136A1 is a star that defines the extraordinary. It forces us to recognize the limits of human imagination, the power of physical laws, and the delicate balance that governs even the most extreme objects. In a 136A1, we see a star that is both titanic and temporary, brilliant and fragile, a shining illustration of the awe-inspiring complexity of the universe itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.